Hello, everyone, and welcome to the webinar. Please take a moment to respond to the poll on your screen. How many individuals are attending this webinar at your location? If there are more than 5 in the room, please enter the number of attendees present in the questions box. We will begin shortly. Thank you all for answering that poll. And hello, everyone. Welcome to EPA's 17th Annual Drinking Water Workshop. We are very glad you could join us today here for the training number 1. And I will now turn it over to Mike Finn to introduce our speakers.
All right, good morning, everybody. So you got to see my picture first. I am with EPA's Office of Groundwater and Drinking Water in Washington, and I will do a couple of presentations today. Also joining us, Eugene Leung, who is with the California Water Resources Control Board, Jason Minnick with Pennsylvania Department of Environmental Protection, Karen Sklenar from the Cadmus Group, a contractor for EPA, and Andrea Traviglia, I messed it up again, Traviglia from, losing voice too, US EPA in Region 1 in the Water Division. All right, and then we'll go to the next slide. All right, what did I already started off in the wrong place, Mackenzie? Are you advancing?
Yes, yeah. Jason should be getting control. Perfect.
Okay.
Great. And Jason, yeah, you can take it away. Jason, we can see your slides, but we're not able to hear you. Might be muted.
All right, is that better?
Perfect, great, thank you.
All right, I'll start again.
Sorry.
Good morning. So my name is Jason Minnick with Pennsylvania DEP's Bureau of Safe Drinking Water. And I wanted to thank EPA and ASWA for inviting me here to talk a little bit about Pennsylvania's e-inspection app. We have an e-inspection app, and one of the things I want to talk about mainly today is how we use that app to help us deal with different treatment processes and kind of looking at data and storing data during our sanitary surveys. There we go. So our app, we started development in late 2017, and it kind of went from we weren't even talking about this, so we were in full-fledged development really quickly. We were going to be DEP's second app, inspection app using an iPad format, and we were going to be actually the first one actually developed by DEP contractors kind of in-house. So it took a little longer than expected. We thought we would have the app by the end of June 2018, and it was actually October till we were rolling the app out and doing training in our different regions. And our app has inspection modules that cover all 8 inspection elements. Currently, we have over 20 modules to do that, and there's over 1,500 questions in those modules. And you'll hear a lot more about that in a second. And another thing to note, though, is that even with all those modules, all those questions, we're still not finished this development. At least we don't think so. We have some additional modules we'd like to add, and we also would like to add additional features as well. So what the app currently can do, it allows inspectors to access inventory information and violation data pretty much from anywhere that they have an internet connection, or they had an internet connection and were able to download information into the app. They can view that data pretty much anywhere. It allows them to create an inspection report based on everything that they find during the inspection. It kind of creates that report for them, emailing that report to them, to their supervisors, and to the water systems, as well as storing those reports in our data system. Creates a separate document that has all of the module question answers and our tables, so that gets stored as well in our data system, emailed out to the supervisors for review. If you take any pictures as part of your inspection, it will add those pictures into a separate document with any labels that you may have on them. Automatically will create violations that are identified during an inspection as part of going through the modules, or just identified during the inspection other ways. It would create those violations automatically, put them in our system. And it also will update then PADWIS and EFACS, which are our two big data systems. We're a SIDWIS-free state, so we have PADWIS for our drinking water data, and EFACS stores inspection and some of the violation data. So updates will happen automatically to those applications, so field staff don't have to return to the office to make those updates. So let's jump into the app now. This is what we call the dashboard. It'd be the first screen that you would see. There's lots of information on here. There's lots of information available in our app that we're just not going to have time to talk about today. But the information there in the middle, this is where it would list all of the public water supplies that we currently have information on the app for those water systems. So right now I only have one, but you can kind of download this information about as many systems as you want. And once you download that information, you don't need an internet connection anymore to view any of that data, or really to conduct an inspection at that water system. So once we decide we're going to do an inspection, since that's what we're really talking about today, we kind of jump into inspections. Pennsylvania, we have several different kinds of inspections, probably like most states do. Sanitary surveys for us are actually called routine complete inspections. So that's what's listed here. But we also have the other types you see there as well. So what you do is you select the type of inspection you want to do, and then you select the number of, we call them sub-facilities. Most other states just call them facilities. Those are your sources, your treatment plants, storage tanks, those types of things. You select all of those that you're going to inspect, and then we would move to the next step. But before we do that, if you're going to do a routine complete inspection or a sanitary survey, all of the facilities are automatically selected. The idea being that if you're doing a sanitary survey, you need to look at all the facilities associated with that water system. So that's automatically done for you. Once you make those selections, you jump over to the Findings tab. And the Findings tab is really the meat of the inspection. And there's, again, a lot of things that you do here, but what we're going to concentrate on are the modules, and then we're going to briefly look at field samples. So if you hit the module tab, you'll see a list of several different modules, all the modules that we have available. And you go ahead and select the module that you want to do, and you also then select the facility that you're going to tie to that module. So every module needs to be associated with a facility. And if we're doing a sanitary survey, every facility needs to be attached to at least one module. Again, we want to make sure that you are doing a module for each facility, so we know that that's a thorough, complete inspection that's being done. So once you make all of your selections here, we can move on to actually seeing the modules. But before we do that real quick, again, we're talking about treatment plants today. We have several different treatment plant modules. We have a general module, as you see there, it's called 2A, but then we have several additional modules that are kind of treatment process specific. And we'll look at one of those a little later, but just note that we have several different treatment process modules, and that is actually one of the things we want to continue to build on, is getting some more treatment process modules. So we select all of the ones we want to use, we hit the next, and it will build those modules for us. You come in here and you actually start to see the modules. You start to see the types of questions that we have. There's really several different kinds. We have standard yes, no's. We have fill in the blanks. Other places you'll see dates. And we also have some drop downs. And examples of the drop downs would be like when a procedure is done. Is it done daily, weekly, monthly, quarterly, that type of thing. So we have all those different types of questions built into our modules. If you notice here with this question, the answer no is shaded red. So that identifies to us that that would be a deficient answer. Some of the questions don't have deficiencies associated with them, as you can see, like with this one. But up here, if you click that deficient answer, what you're going to get is another pop-up window. And what this pop-up window contains is all of the, or additional information about that deficiency. So it kind of gives the inspector a little more information about why that's a problem, with that deficient answer. And additionally, then this information is going to automatically end up in our final report, and you will see that at a little later in the talk. But so this is all standard information. We have standard language for all of our 1,500 questions. If it would be what we would consider a violation or a legal citation would be here. You'll see one of those a little later. There's also a remarks field here. And basically, so if you want to type in any additional information specific to this question, specific to this situation, you can type it in here and it will also be transferred right over to your inspection report when you're done. So moving on, just a little more about questions. You'll see here, this here is a question, does the source have a pump house? So if you answer that no, the source does not have a pump house, what happens automatically is all the questions related to pump houses are grayed out. So the inspector doesn't have to answer those questions. Those questions also won't show up in our checklist when we're, after we submit the inspection to try and, so that does two things. It doesn't make the inspector have to click additional boxes if they don't need to. And it also then keeps the PDF a little shorter. And those are spread pretty much throughout all of the modules. And you can see there's a little asterisk in the corner that basically tells you that if you answer this question this way, some number of additional questions below it will be grayed out. And that's a really important feature that kind of saves us some clicks and saves us some time. I guess kind of jumping back real quick, we don't necessarily expect the inspector to sit there with their nose in their iPad the whole inspection, just asking questions and clicking boxes. The idea is, as the inspectors become more familiar with inspection processes, because we do have a lot of newer inspectors in Pennsylvania, the inspection is more of a conversation as they're going through it with the operator or whoever they're there with. And kind of the checklist, they can cross off questions, answer questions as they go, but also then at the end of that inspection, they kind of can look through it and see if there's anything that they didn't talk about. I don't necessarily expect them to, and we don't expect them to stand there and be like, does this source have a pump station? And they get an answer from the operator, then they click that box. That's not really the idea. The idea is to use this as reminders and just double checks to make sure that they're capturing all the information they should. Just wanted to kind of throw that out there. Another thing that we can do inside the modules that you'll see here, if you swipe on the actual question, you can attach pictures to it, you can attach files to that specific question, or you can attach comments to that specific question. And the neat thing about that is then when you're building your inspection report at the end, the pictures that you take will automatically be labeled with this question and with this sub-facility ID or facility ID, so you know where you took that picture. Same thing with a comment, there'll be a tag for this question, so you know that this is where that comment came from. And then you have the ability to just copy and paste that comment right into your inspection document at the end, and you'll see that here in a minute. So let's actually look at a treatment module. This is the membrane filtration module. And the first thing you probably note is that it's all red. Like I said before, with a complete inspection sanitary survey, staff have to answer every question. So this inspection that you're looking at here is actually a different inspection, and it is a sanitary survey. And all of the module questions are red because they haven't been answered yet. As soon as you answer a question, it turns white. And the idea there is it makes it really easy for the inspector to kind of scroll through the module and see which question hasn't been answered yet. The other thing that's a helpful little tool is all of the modules that are completed. So when every question is answered, a little check mark comes up here. So this way the inspector knows I'm done with this module. I don't necessarily have to go back to it. But the module F or 2F is not done yet, so I need to look at that one. So again, lots of questions about membrane filtration specifically. These are all about pre-treatment. Just kind of moving down through this, this module, scrolling down through. We have another question here, and this question was actually, yes was the deficient answer. Is the plant chronically failing to calculate the CFE turbidity every 90 days, turbidity meter every 90 days? And then some additional text as well. So if we say, yeah, they're failing to do that, we click that, we end up with another one of those pop-ups. The thing with this pop-up is it's a little different. You'll note over here, there's a statement that says violation, and a checkbox is checked beside it. That means that this situation, not calibrating your turbidity meter every 90 days, is considered an actual violation of our regulations. You come over here in the standard language, it kind of tells you the type of violation it is. It goes through the situation again, and then it gives you the regulation that's being violated. Again, and the regulation citation is right there. Those citations get put right into the inspection. So this inspector doesn't have to remember what the citation is to write it down or anything like that in the inspection. It's automatically created for them. They also have, of course, the ability to put remarks in. So back into that, that module again, one of the other things, other features I wanted to show you guys is some of our questions have tables attached to them. So tables obviously make it easy for us to record information that we find out during an inspection. So you'll see this question here, there's a little table icon beside it. So you can either access the table by clicking the icon or just by clicking the yes answer. In this case, it brings up this table. We have several tables. This one is where the inspector would note a membrane unit ID and the date that a clean in place was done. And they can add as many rows as they want, depending on how many modules this or membrane units this treatment plant has. Maybe they want to record several of those clean in places to get an idea of how frequently they're occurring. They can put all of this in this table. Table is saved. Table becomes part of the checklist document at the end. Just finishing out this module, you'll see that we have 113 questions specific to membrane filtration. Not all of our modules have this many questions, but several of them do. And it's kind of just to show really how thorough we're looking at things, or we expect the inspectors to look at things during inspections. The other thing to note on here, every module has a section called Other Significant Deficiencies at the end. It's kind of a catch-all. If there's a situation where we thought a significant deficiency could occur at this type of facility, but we just didn't capture it in one of the questions above, we kind of add it to the end. So every module will have at least a couple of those questions at the end. It's kind of just that like catch-all at the end. So that's the module questions. That's our modules, pretty briefly. I wanted to show you guys just how we capture field samples or capture information about field samples as well in the app. So field samples is another tab on that findings screen. You have the ability then to select the facility that's being sampled, the date. You have a drop down for the parameters that we can sample for. What's the results you got? If it's actually associated with a sample that gets submitted to our laboratory, you can put that information here, and then you just write a description as well. And you add it, and you can add as many as you want. And you'll see when we do the inspection report, they all end up at the bottom of the inspection report. Once you're really done looking at things as part of the inspection, you've talked about any other violations, whether they were noted during the inspection or maybe they were monitoring and reporting type violations. You've gone through all of that. Then you come to the summary tab, and there's lots of things that can be done in the summary tab. You can review the pictures that you took, decide if you want to keep them, decide if you need to add any additional labels to them. You can add additional files to the inspection, note whether compliance assistance was given. And then you come down to the general comments, which is exactly what it sounds like. This is where you can type in or use dictation to create a narrative for your inspection. If you wanted to, these remarks down here, these are the remarks that we took on specific questions. So you can see them as kind of a reminder that, hey, you put this remark in, and if you want to keep that remark and you want it to be part of your general comments, all you do is copy and paste it. That remark shows up in your general comments. Once you're done with your general comments, you go on to the next pieces. You have enforcements, which we're still working on. It's basically to create enforcements, including NOVs automatically, and that's still a work in progress. And you get down here to finalize. This is where you will select your inspection results, which are limited by the findings of the inspection. So if you found violations, you can only have inspection results that are associated with violations and things like that. How long were you on site? You can select the name of the person who's receiving this inspection. And before you have them sign it, you can actually preview the inspection report with them. You'll preview the PDF so they can see what it's going to look at. They can see the violations that you noted, and they can kind of agree to accept that report. Once they sign it, the last thing that you do is you hit submit. And once they've signed it, you can't change the inspection anymore. So you hit submit, and let's real quickly just look at what an inspection report's going to look like. This is the top of the report. Some of this information is generated from the inspection. Some is generated from just our data system. You move down through, first section is violations. So if you identified violations in your inspection, they show up right here. The citations are here. The standard language for the description is here. It's all already put together for the inspector. And if you added any comments or remarks, they would show up there as well. Next section is minor deficiencies. So in Pennsylvania, if we have significant deficiencies, we call those violations in our data system, and we track them as violations. We kind of always have. But if there's something that doesn't come up to that level of what we would consider a violation, it's listed as a minor deficiency. So that's the next section of the inspection. Again, standard language is already here for the inspector, tells the facility that it's associated with, tells what the deficiency is. That's not good.
Hey, Jason, this is Mackenzie. Is there anything I can help with?
I don't know. Am I still sharing a screen?
Yes, we can see the presentation, but it's not in PowerPoint mode, and it looks like the presentation might be behind it.
Okay.
If you'd like, I can reshare your slides and it can reset.
But let me just see. So every time I touch it, it goes black on my side. Anyway, hold on. Yeah. Is it possible to switch over to you? Do you happen to have mine open, my presentation open?
Yep.
Why don't we do that?
All right, great.
Okay.
There we go, and let me move forward.
One more. Okay, this is where we were. So we just talked about minor deficiencies. Again, they don't raise to the level of a violation for us, but we do note them. Next slide. Next section is your general comments. This is whatever the inspector put in, including the copy and pasted comments. It all shows up right here. Next slide. Last piece, or last sections, field samples. It shows up real nice here, telling you the sub-facility that was sampled, what the parameter was, what the results were. And you would have as many of these rows as samples that were collected during the inspection. It's all documented right here for the inspector. Last part there is the signature section. It tells you who received it. And in this case, I noted it as we weren't actually able to get a signature. So you can submit the inspection without a signature if you have to. And you just write a description of why. You know, maybe that in this case, the responsible party left. The person on site was just unwilling to sign the document. Whatever that is, you can note it here, and then it also tells you who the inspector is, and that is basically whoever's logged into the app. Next slide. So this is our checklist document, that internal document that just goes to the supervisor and our file. So this is all of the answers to all of our questions. And no matter what type of question it was, the answers are there. You know, there's yes, no's, there's dailies, and dates are shown there. But any type of question that we got, the answers will show up. Next slide. Same thing for any of the tables that we built during the inspection. So here's just 3 examples of some of the types of tables that we have. If you answer table questions as part of a module, they will show up here. And again, this way you're recording whatever data you collected during the inspection. And it's all a fairly easy process to record all that and document it in this document that we keep as part of the inspection record. Next slide. So that's kind of the inspection process. But one of the other things that it allows us to do in our central office over time is really conduct like audits of the inspection process and audits of the app itself, really. So we could look at, you know, a specific question. So right here we're looking at data for, does a well have a sanitary seal? So any inspection that was done in 2019 that answered that question, we pulled the data for it. As you can see, overwhelmingly the answer is yes. So in my mind, what this can tell us is that maybe having a sanitary seal well cap isn't a big problem for the water systems. But if it came in and the majority of these were no, that would tell us, well, you know, maybe this is an issue. Maybe is it a training need? Is it a compliance, more of a compliance issue that we have to handle a different way? Should we be creating some newsletter articles talking about sanitary seal well caps, things like that? If you see a lot of unknowns or NAs, maybe that tells us internally with development of the app that maybe this is a bad question. You know, if NAs answered a lot, maybe we need to revise that question. And if unknowns answered a lot, maybe we need to do some training for our staff so they understand what this question means a little better. So it's allowing us And we're just getting started on this process. But it's going to allow us to really dig into the inspection process and kind of review how it's working. Next slide. So that's really all I have. I'll take questions at the end with the group, and that's my information if you wanted to reach out to me directly about it. Thank you. I'll turn it back over.
Great,
Thank
you.
Jason.
And
All right. What like something is popping up here. What are you seeing, Mackenzie? What are we seeing?
so I can see PowerPoint, and if you can just go up to slideshow up top, and then
There we
from
go.
beginning. Perfect.
This is not a day for a slow computer. All right. Part of our goal here today was to cover some things that those of you who have been to our sanitary survey trainings or other sanitary survey trainings, we don't get to cover in a lot of depth. So hopefully a couple of these modules will give you some more information, some things that we don't always cover, some things that people don't see very often, or might be faced with for the first time. So hopefully this will give you some help with getting through those. So talk about membrane filtrations and basically evaluating those membranes as part of your sanitary survey. And this I won't read through. This is the required disclaimer language that those of us in EPA are required to use. It's up there. I'll leave it there for a second. All right. First, some of you may be familiar with this, but a little bit of background. The National Primary Drinking Water Standards regulations require for surface water sources 3 logs of Giardia lamblia removal and/or inactivation, 4 logs of virus removal and/or inactivation, and 2 logs of cryptosporidium removal under the current regulations. And surface water treatment is based on the multi-barrier concept, a combination of filtration and disinfection as a technique for public health protection from pathogens. Those treatment technique requirements are met by the filtration performance standard, which is generally turbidity, and inactivation, usually called CT. Membrane filtration is considered an alternative filtration technology. So the removal has to be demonstrated to the state or EPA, and then the state EPA sets turbidity performance standards and other performance standards for that treatment. What is it defined as? A pressure or vacuum driven separation process in which particulate matter larger than 1 micron is removed by an engineered barrier, primarily through size exclusion, and which has a removal efficiency of a target organism verified through a direct integrity test, which we'll talk about. That's the regulatory language. And membranes generally, for our purposes, include microfiltration, cartridge filtration, we'll talk about them in a minute, nanofiltration, and reverse osmosis. A cartridge filter that meets the definition of a membrane has to be subject to direct integrity tests, and in that case, it's considered a membrane cartridge filter. These do not consider any filter that relies on mechanisms such as adhesion or accumulation of a fouling layer, which we'll talk about in a little later, bag filters in particular. So what are we looking at in terms of what these filters can do in helping us deal with microbial pathogens? And again, this is just a caveat here. This is not EPA regulation. This is not guidance. These are basically what's you'll find in the literature, what states are awarding, and practical experience from those of us that are dealing with it. So as we go down the left-hand side, the removal potential increases. Microfiltration capable of Giardia, Cryptosporidium bacteria, but not viruses. That's much too large for a virus. And then as we move on down, narrower and narrower, smaller pores will begin to increase. So ultrafiltration, you get some virus removal, and the nanofiltration or reverse osmosis are probably capable, and we'll talk about the probably part later, of at least 4 logs of removal of all the above, Giardia, Cryptosporidium, bacteria, and viruses. And then bag filters, as we mentioned, they're not considered membranes, but we'll talk about them a little bit because people might be exposed to them. So let's talk about the first 3, microfiltration, membrane cartridge, ultrafiltration, and what they're capable of removing and how they remove it. So an intact membrane, any 3 of those, can reject Cryptosporidium, Giardia, and bacteria. So as we mentioned, in microfiltration, you're in the 0.1 micron, and that's much larger than viruses. So you're not getting any significant virus removal through the microfiltration. Ultrafiltration membranes, smaller pore size, an order less, and you are getting some virus removal. Viruses vary in size, but you are getting some removal there. And the principal mechanism is size exclusion. So those pathogens, particles are captured in the voids, in the polymer that make up a semipermeable membrane layer. Again, moving down in size, intact, reverse osmosis, and nanofiltration. The differences between those are kind of depend on people's opinions sometimes. They're very close in terms of size. They can reject a virus, such as a poliovirus, and that small. Again, the principal mechanism is size exclusion. It's just a tighter membrane captured in the void spaces. And the size here, molecular weight cutoff, which I won't try and explain, it's basically a measure of a molecule. For organic molecules is 1 to 300 Daltons, which viruses, bacteria, and common pathogens are much larger than that. There's also, if you look at in our operations manual or the literature, there's possibly some charge repulsion where the viruses have a negative surface charge that may keep them passing through the membrane, possibly adsorption on top of the membrane. And then as we talked about the charge part, there's some information you might find about membrane aging that as the membrane ages, it may become more negatively charged, a little bit rougher, and increase the adsorption of pathogens. So just quickly what you might find, depending on what you're looking at, the plant is trying to accomplish, some level of protective screening before it, a microfiltration, ultrafiltration membrane, and then either onto disinfection if that's all your target is, or onto RO nanofiltration. Generally, you'll find some level of fine screen membrane filtration in front of ROs to protect the membrane, to protect the RO membrane. All right, so I'll put this in the context of meeting surface water treatment rules. So long-term 2 enhanced surface water treatment rule for membranes requires that the removal efficiency be established through a product-specific challenge test or through direct integrity testing, which we'll talk about. Direct integrity testing has to be periodic. Recommendation is once a day, and most utilities do it that way. And then continuous indirect turbidity monitoring, continuous indirect integrity monitoring, I should say, during operation. And the log removal credit for that membrane, whatever it is that demonstrated through the challenge test or the maximum log removal that can be verified by a direct integrity test. All right, so generally we're looking at, this is again rule of thumb, what these membranes are capable of. 3 log removal of Giardia for membrane filtration, ultrafiltration, microfiltration, ultrafiltration, 2 logs of Cryptosporidium, and essentially no virus. And for the tighter membranes, RO and nanofiltration, they're capable of more than 3 log of Giardia, 2 logs removal of Cryptosporidium. We'll talk a little bit about the virus removal issue for those membranes in a second. And then the remaining virus requirements are met with disinfection, which satisfies what the surface water treatment rules focus is, which is a multiple barrier approach to protection against microbial pathogens. I talked about the virus removal for a second. If you look at what the size of an RO and nanofiltration membrane, they should be capable of removing viruses, but many states really only allow a 2-log virus removal credit. And the reason for that is usually that the indirect integrity methods are not sensitive enough to find a breach in that RO that may allow passage of viruses. And moreover, the pressures required for direct integrity testing for those membranes is quite high. So as you look, and they will possibly damage the membrane. You look at the number there, 700 psi for 0.01 microns. And then again, the 2-log virus inactivation can be easily met with low disinfectant doses. And again, this approach, is consistent with the surface water treatment rules, where you have multiple barriers and you also have another level of reliability. All right, quickly, challenge tests. What is it? A challenge test is an evaluation of the membrane in its completed form. So what you're demonstrating is the target organism, whatever that is, can be efficiently removed. It is a one-time product-specific test. Generally, the manufacturer is doing the challenge testing, and that test establishes the maximum removal credit that's possible. And the basic procedure is to spike some feed water with a target organism, or usually a surrogate, and then measure the log reduction in concentration. So log removal value is the log of what you're feeding versus minus the log of what the membrane product is. Once those challenge tests are complete, a quality control release value is established. And what that does is sets a quality control for all the other membranes that are manufactured, the same membranes. So each membrane, each module is not subject to a challenge test, but they do have to meet whatever is established as the quality control release value. And it's important to note that product modification is probably something to pay attention to. They really need to be retesting it because obviously you can't see what's inside a membrane, and the membrane that was challenged may or may not be the same. And then regulatory requirements stepping in here. The challenge test must be reported to the state under the long-term tool rule. And there is an allowance of old test data if that test conform to what the current requirements are. So what else? They can be conducted on full or small scale modules. And I mentioned challenge particulates, the target organism, crypto-oocysts or viruses, or more often surrogate particles that are not removed no more efficiently than the target organism, and they have to be discretely qualified, in other words, counted. And then there's a limit under the surface water treatment rules that the maximum feed concentration cannot exceed that that number, which is filtrate detection limit times that. And the test has to be done under maximum design flux. So, all right, and why are we testing these? Because loss of integrity means a passage of pathogens. So the parts that can be damaged or wear out includes O-rings on the membranes, glue line seats, leaks, oxidant damage. Some membranes are capable of dealing with oxidants ahead of time, others are not. The back pressure from the permeate is too high. Something pushing back will damage the membrane. And then there's obvious pipe leaks, systems leaking. The whole system is under heavy pressure. The challenge test sets the operating conditions, and if they exceed those operating conditions, the potential is to damage the membrane. And then damages due to particulates and fouling. I mentioned we looked at our diagram where you have pre-filters ahead of it to minimize that kind of damage. So, all right, what is a direct integrity test? Periodically verifying the performance of an installed operating membrane filtration system. So the methods that are used for that test are flexible, but must meet requirements for resolution, sensitivity, and frequency. The most common, which many of you may have seen, is a pressure-based test, applying pressurized air to the membrane and then watching the pressure decay and seeing if that meets criteria. And then similarly with a marker-based test, which are a little more complicated, we won't cover those this time. And again, the direct integrity test establishes the control limits and the sensitivity limits of the test. Determine that whether the membrane is operating within those limits and meeting the removal credit assigned in the challenge test set. There's a pretty big US EPA membrane guidance manual on the web. You can find it. It was written a while ago, but most of the information is fairly current. So a membrane can be tested either physically, as we mentioned, pressure decay or vacuum decay, similar. The last two, diffusive flow tests and water displacement tests, I've never seen. I don't know if anyone uses them. There's been a lot of interest in concentration-based tests. It's basically spiking something, particularly for reverse osmosis membranes, where the challenges are a little bit more of a challenge to demonstrate the log removals. And then an allowance for a manufacturer developed test that satisfies the criteria under the long-term 2. There's a 2 missing there, speaking of quality control. And then what are we doing after that? We're doing continuous integrity monitoring, just like you use continuous monitoring on a conventional filter or other types of removal processes. Basically what continuous means, consistent with what we place in other rules, is every 15 minutes. Monitoring some aspect of the water quality that indicates removal of particulate matter. Each membrane unit needs to be monitored separately. And the criteria, again, under the current rule, is 2 consecutive exceedances, whatever the state sets as the trigger, require a direct integrity test. So the membrane is removed from service and then placed under pressure, placed through the entire direct integrity test. And then if leaks, others are found, it has to be repaired before it's put back in service. And what does it do? It provides a real-time indication of membrane integrity, albeit turbidity is not very sensitive. In this case, pretty large particles, but it is at least an indicator of when something is wrong with the membrane or the membrane has a problem and needs to be checked. And I mentioned the default method, and this is under at least the current rule, is turbidity monitoring with 0.15 NTU as a control limit. It's not very sensitive to small breaches, but it is one method of determining membrane failure or membrane failure starting. Particle counting is sensitive to smaller integrity breaches, but the equipment is obviously more expensive, and you need some base level particle count to establish whether the particles found are problematic or not. Conductivity monitoring, there's been a lot of discussion about that. It's not very sensitive either, but I know some of the membrane manufacturers are trying to find ways to use it as for indirect integrity, and there may be other methods as well. So if they're going to use another method, it has to be approved by the state. It has to allow online continuous monitoring. Again, each membrane unit has to be monitored. And any significant fluctuation in the parameter they're monitoring should be indicative of a breach in membrane integrity. And then whatever that method is, it has to be sufficiently sensitive enough to allow setting some kind of control limit. Talk a little bit more about RO membranes and what the issues are with indirect integrity monitoring. Particles counting, you're counting fairly large particles, greater than 0.5 micron. which is obviously much bigger than a virus. We mentioned turbidity is not a very sensitive indicator. Sulfate monitoring has been suggested in other places, but the online systems are very expensive. Conductivity monitoring as well, fairly low resolution as well, not exactly a tight indicator. Same thing with TOC monitoring, fairly low resolution. There's been some discussion about using all these, some of these in combination, but obviously adding to the cost. And if you have three different measurements, how do you interpret the data, and then what actions do you take after that? So the membrane module specifications, the direct integrity test, all goes into setting operating conditions for the membrane you're going to see in a water treatment plant. So that's the membrane area, which is built in, obviously. Maximum design flux, so that's what the maximum the membrane can see in terms of passing through it. Maximum feed, that would be flow. Transmembrane pressures. Other operating constraints that are needed or you might set, or limitations found in the challenge testing, including pH, temperature, things like that. Setting direct integrity test parameters. Non-destructive pressure testing results and the quality control release value that we talked about. And then how is the membrane plumbed in the system? Is it similar to whatever configuration the manufacturer used to test the membrane? So what are we going to look at when we go for a sanitary survey of those membranes? We're going to look at whatever comes up first. Pre-treatment processes. Is it the same model as approved? Same manufacturer, same model number that was approved in the first place? Are there new raw water sources or new intakes that might require reconsidering whether that membrane size or operation is appropriate? What is being used for indirect integrity monitoring, and what criteria trigger a direct integrity test? Membrane cartridge filters are basically replaced, so there should be some level of replacement schedule. Spare parts, obviously. What is the backwash process and how is it completed? It's not a little different than what you see in a conventional filter, but there is a process that the operator usually initiates automatically. And just as you look at a conventional filter, how are they doing it and how often are they doing it? How are they controlling pressure and flow? And then what you'd obviously want to see in any water treatment plant, the alarms, the alarm notifications, how they respond, and does it automatically shut down or some other action. Again, all these operate under pressure, so the process pump system is important. And then as we talked about, some membranes are okay dealing with a disinfectant, others pre-disinfection can damage the membrane. Again, what are we reviewing? Is it the same as you approved or was approved, including the pre-treatment system? What criteria is the utility using to replace membranes? We talked about alarms, notification. Is there a filter to waste or a filter bypass process? Is it approved? Are cross connections identified and labeled? And then ask the operator to describe any filter to waste, or if they use a bypass process, how is that done? And then this is not necessarily sanitary survey, but there are always considerations of the RO reject brine disposal. It's very concentrated, and some utilities may not be able to discharge it. They may have to hold it on site, which might limit their process. So what else do we want to look at? Membranes need to be clean. What's the criteria for cleaning it? Hours in service, or is there some monitoring criteria they use? Some membranes do not permit reverse flow, our own particular, so they can't be backwashed. Ask the operator to describe the cleaning process and in particular what chemicals they're using for cleaning. They're usually using something, some chemical as a cleaning aid. What happens when they take a module out of service to clean it? How do they deal with the flows that you may have set? What are they using for treatment chemicals type? Where is it applied? If you require or advise third party for certification, such as NSF. How are the treatment chemicals dosed, as you would ask in a conventional water treatment plant as well? Flow paste. How does the operator verify the dosage from an automatic feed system? Example being a pump catch. And then chemical feed system reliability and redundancy. So standby pumps, can they repair the chemical feed system on site? And like all their other processes, there's got to be some kind of process control monitoring. Again, the challenge test or the validation establishes a range or limit of operational parameters that are associated with that demonstration. So the membrane should be operating under the same conditions that the challenge test provided. So that's permeate flux, the feed pressure, pH, if that's an issue, feed water temperature, and then the recovery rate ratio, which I won't get into here, but basically that's the rate of the permeate divided by the feed water, so entrance versus exits. And then quickly here, like you would look at any water treatment plant, any process. We talked about the multivariate concept. So the disinfection that comes after a membrane, do they meet their inactivation requirements using CT or UV dose, whatever they're measuring? A minimum residual, which obviously the membrane doesn't provide. Detectable residual, similarly. And then again, the turbidity limits that you would have set in approving that membrane. Is there any corrosion control treatment? I'm not talking about necessarily compliance treatment, but internal corrosion control treatment. And then obviously, the lead and copper results. You are making fairly aggressive water here. That's probably an important point to mention as well. You're moving a lot of things with a membrane if it's an RO, and you can make some very aggressive water. Quickly, bag and cartridge filters, there's really not a lot to talk about. I mean, these are fairly simple processes, mostly small system technologies. You basically have a fabric bag out of nylon or polyester in some kind of housing, and water is passed through that. And unlike membranes, as I mentioned, removal is particles adhering to the fabric. So it's not cleaned, it's not backwashed. When some kind of pressure loss criteria is met and should be measured, and simply the filter is replaced. So in other words, it has to be shut off. So a question to ask would be, what happens when you have to replace it? Is there a second filter? Is there enough storage? What do you do when you take the existing filter housing apart and replace the filter media? Fairly sensitive to overpressurization. There are gaskets in the housing that overpressurizing them can damage them, cause bypasses and leaks. As with other similar processes, they're not, again, not really membranes, but they're not conventional filtration either. So the removal credit is based on a challenge test. Under the long-term 2, there's the quality control. Again, we're missing a 2. Allows a 2-log removal with a 1-log safety factor for cryptosporidium and for a single filter. And for filters in series, there's an allowance for a 2.5-log removal with a higher half-log safety factor. That's what, for those of you who've never seen one, again, the very small system technology, usually that's what it looks like. You have an inlet, a meter, hopefully, a roughing filter generally to protect whatever the bag filter is. 50 microns, obviously very large. Another roughing filter, and then the bag filter, one micron bag filter. And the important point, you see the pressure gauges, which are a little bit fuzzy, but an important thing to look for, because again, pressure changes, overpressurization will damage them and compromise the removal. I mentioned this, minimum of 2 filters if you're going to try and provide continuous water service. Pressure relief someplace, and overpressurizing the membranes, particularly with on and off cycling, can damage them, cause bypass. So what do you want to look for in a sanitary survey? What type of pre-filtration is used? Something ahead of the smaller bag filter, protecting it. What is the micron rating? That determines really what kind of credit you're going to give it. As with others, there should be a manufacturer's challenge test and cryptosporidium for the filter, and same housing. This tends to be a problem for smaller systems in particular, when the filter model changes or they have to fix something and it no longer resembles either what you approved, or the filter itself is not an approved filter. It's a different model. I mentioned that below. Again, is that model still available? Do they have replacements? Some systems face some challenges, and the state finds them when the manufacturer stops manufacturing that particular model due to lack of demand or changes in their process. Pressure gauges in place. I mentioned this. Very important, because the pressure, if anything, will damage the membranes, damage the seals. Again, what happens when you have to take one out of service? Really important, especially for smaller systems that start and stop. If it starts and stops or continues to cycle and pressure surges, can overload or damage the membrane. And then how do they meet their remaining treatment requirements? Once they obviously they're not getting a lot of removal, so they need to meet their remaining treatment requirements with other filtration or disinfection. And what you look for in any other system, the alarms, the operator notification, usually these are operated left remotely, or the operator is not present. So important questions to ask is what happens when something goes wrong. Oops. And then we will move to the quiz questions.
Great, thank you, Michael. The first poll has been launched. And it is the log removal credit awarded to a membrane is based on, and then please select your answer. And it looks like we had 66% of the attendees say A or B, whichever is lower.
And that is correct, whichever is lower.
Great, we'll move on to the next one. Which of the following membrane technologies are capable of removing cryptosporidium, giardia, and viruses? And we had 67% say CRO and nanofiltration.
And C is correct.
We'll move to the last poll of this section. So when a bag filter becomes clogged, it is, and please select your answer. And we had 66% say removed and replaced with the same model approved by a state.
And that is correct. 66% of you are right.
Great, and that is our polls for this section.
And we were scheduled for a break right about now, 15 minutes. If we could do 10 minutes, because we're running a little bit behind, that would be great.
Should I be starting up?
You're all set to be.
Okay. So welcome back, everybody, to our training this morning. So this afternoon, for those of you in the East Coast, the topic that I'll be covering is for the Sanitary. Why is it doing this? Okay. The topic I'll be covering today changed, and I'll be providing you an oversight of the ion exchange treatment, so that when you go out on your server, you'll be able to ask good questions and the treatment. So I may be familiar with treatment water softener at home. So it's based on water, but depending that you put in the, you have different being able to contaminants. General design of it is on the right. It's like water coming in comes in, so that the water across the under drain system that, and then goes into, then you'll be able to have the treated water. The different type of resin generally we have is the two charges. The cationic resin is for taking out positive charged contaminants, and then the anionic is for taking out negatively charged ion exchange. So depending on the application we have, it's possible to have both types of resins in series. So in some cases that you could possibly want to soften the water first before you remove the contaminant. So it's for some system that you can actually have both cationic and anionic ion exchange running series. So it goes after one treatment before. The resin, the key difference for the different system is that the resin can be nowadays, with a softener at home, generally you have it regenerated on-site. For some businesses, you may see it that they don't have the facility to regenerate on-site, so they take it off-site for regeneration back at the resin company, and then they bring back new steel vessels, and you see that a lot in businesses. And then last but not least, increasingly, depend on some of the contaminants, especially the ones that have really low MCLs or maximum contaminant levels, you can just use the ion exchange resin once and then you dispose of it. So I call those just single-use, single-pass media. You can find out some more general information on the link provided, and that will take you to the drinking water treatability database that EPA has put together. So in drinking water treatment, as I mentioned, the most common form of ion exchange is used at home when you have water softening use. And cationic ion exchange resin is used for softening. And when we use salt to exchange, so the most important thing is that the most typical that we use is like sodium chloride, so just regular table salt, or potassium chloride are the two of the most commonly used salts. Sometimes, like in softening applications, you see that people put in potassium chloride instead of sodium chloride because they want to keep the sodium level in the drinking water low, especially for people with higher blood pressure. They don't want to add more sodium into the diet if they can help it. So that's why they use potassium chloride. A saturated solution is used to regenerate the ion exchange resin. So that's when you see in, if you're familiar with a softener, you dump the salt into a basin and then they just fill it with water. So with water soaking in the salt solution, it will create a saturated solution, and that's what you use for regenerate the ion exchange resin. In softening, so you're either exchanging sodium ion or potassium ion, as I've mentioned, and then you use that to exchange out the calcium and the magnesium that is in the water that they cause hardness or film that you see on your dishes. So water is softened by exchanging the calcium magnesium ions with either sodium and potassium as the water passes through the resin bed. And as you know, over time, you have limited exchange capacity because once you have charged up the ion exchange resin, you can use up all the sodium and potassium, that capacity that you have with calcium and magnesium, and the calcium and magnesium will start passing through the water again, and then you will no longer have the softening effects. So that's how the basic for ion exchange works. So here's a typical package water softening system that you see. A lot of places that some people may have it at home. You have your brine tank on the left, and that's, as I've mentioned, that they put in the salt, the large crystals of salts in there, and then the system just automatically fill it with water and let it soak to become a saturated solution. And then it goes into the ion exchange resin filter on the right. So in this case, you can tell the water is entering from the top based on the arrows coming down on the resin, and then it's collected at the very bottom, and then it flows back up to the top, and then the soft water is served to the home. This is a very typical setup that people have hard water that they may have at home. So this is a really convenient package system. So sometimes you see that this type of system is very ideal. Maybe it's good to use, just repurpose it for drinking water treatment, because it has all the automated system, everything is integrated in it already. So there is a potential for use such a treatment system for like nitrate or arsenic treatment if you change it to the appropriate resin. One big issue when you're especially treating for nitrates, when you're looking at this type of treatment system, during a softener, when you go through the regeneration cycle, like overnight at 2 in the morning, the system actually allows the untreated water to bypass the system to keep water going, so that if you have to flush the toilet in the middle of the night, even though the system is regenerating, your system stays pressurized and you're able to get bypass water to keep everything going. But that may not be such a good idea for nitrate treatment, because like someone maybe making a baby formula at 2 in the morning, you wouldn't want them to have high nitrate water because that will pose a public health risk. So that's if you see one of these systems being repackaged, the most important part to see if they are able to disable the regeneration cycle so that the water is not bypassed during the regeneration process. These fully automated system, one another key part is it's really dependent on the older system. It's based on a timer setting, so that because for water softening purposes, if you get a little bit of hot water, there's no public health risk, so that may just be regenerated every day or every third day. But whereas the newer system now is actually able to monitor how much water has been used, so it's regenerated based on volume treated. That will be a better setup, so that you can make sure that the water is being treated and the resin is being regenerated at the appropriate time. So resin regeneration. So these are key steps for water treatment, both for softening and for drinking water. Pretty much the resin goes through 4 basic steps of regeneration. First, it goes through a slow backwash. It pretty much removes all the fines and particulate matter that may have been trapped on the resin. So it's just a slow backwash to remove all the solid particles that may have collected on the resin itself. After that, the brine solution that you have created in that solution tank is used to is pushed through the resin. Sometimes on a co-current flow, sometimes on a counter-current flow. There are different concepts, but both of them will work. Just depends on the manufacturing and depends on the designer. But you will see both types. But it's the regeneration is pushing the brine solution slowly through it, so that you'll be displacing all the ions that you've removed from the water. So if you're doing water softening, it'll be pushing off all the calcium, magnesium that you have removed, and then replaced it with sodium or potassium ions again. If you're treating for nitrates or arsenic, you'll be removing the nitrate ion, the NO3-, and then you'll be replacing it on the resin. You'll be pushing a lot of chloride on it, so that it's ready to be exchanged again once it's placed in the surface. So after the regeneration process, you need to slowly rinse it with water, because the solution is extremely salty and you don't want that to be served to the customer. So it's just kind of like slowly using, try to have a laminar flow to slowly push the water, push the brine solution out of the column. And then finally, you have a fast rinse just to push up any remaining brine that you have left in the solution. And that's the basic 4 steps for resin regeneration process. Here, this is one of the biggest issue that I'm not that we need to understand is the waste brine. So you have concentrated waste either from softening or from drinking water treatment from nitrate or for arsenic. The waste brine is usually discharged into the sanitary sewer or the septic system. Locally, you really need to determine if this is an acceptable approach. Like, for example, in California, there's a lot of basins that have excess sodium chloride level, too much salt in the water, so that it is no longer acceptable to discharge this brine into just a regular septic system. So it's really critical for you to find out from your in the state in California with the regional water quality control boards to see if it's acceptable to discharge this type of waste, or the wastewater system. Is it acceptable to discharge the brine would push them over the discharge limits? So that's something to consider. And then, as I mentioned, during the regeneration process for softening, untreated water is bypassed and to soften to keep providing water. But if we're using to treat something like especially for an acute health risk, like for nitrate, that probably should be bypassed and not be used. And you can deactivate it, especially for a system that may have treated water storage tank before it goes in the system. So it's okay to prevent the system from coming on, but you need to have proper programming so the well is not pumping against the deadhead. So here's kind of like the next step for that this is helpful for you to understand. For ion exchange, the most critical part for you to look at is actually just the different types, the preference of ions that will be staying on the resin itself. It's actually kind of like playing favorites. What is the contaminant, and at the relative of sequence, what's being pushed off. So this is a figure that I grabbed from the arsenic design manual that you can take a look at it. And what you can see here on the y-axis is the arsenic concentration, and then on the x-axis is pretty much its time. You can see that the influent concentration for this raw water actually goes all over the place, and this is the ones with the triangle, so you can see that it goes up and come down at times. And then the system is designed based on regeneration based on time and a system usage. So you can see that the arsenic level was pretty high. Once the system gets regenerated here, the effluent concentration from the system stays really low. But once the treatment capacity is exceeded, the arsenic is being pushed back out. So there's arsenic dumping happening because there's some more preferred ion that's pushing off the arsenic. So it's resulting the arsenic can come off of the resin much higher than the influent concentration, because whatever was held before get pushed off. So there's arsenic dumping. So the system after the dumping is going to still continue to operate over the MCL, and they maybe after the big push of the dumping, there's other resin at play, but it's still well over the MCL. It's doing some removal, but it's not low enough. And then once the system triggered into regeneration again, it gets well below the MCL again, and then depends on the timing again, it will go past the MCL, and then it's well over. So it is critical, really, if for this case, if we're using it to operate for arsenic treatment, you can see the big red box here. During that time, the system's actually serving water that's over the MCL, and that's not good. So for us, it would be important for us to determine that the system should be actually regenerated actually around every like 4.5 or every 5 weeks, so that the arsenic will be able to keep operating at this zone, so that the treated water will meet the drinking water standard and will not have this long period of time over the MCL. So the selectivity sequence, as I was saying, that the resin actually play favorites. This is the typical one for regular strong base anionic exchange resin. So these are all the chemical formulas for the contaminants that being capable of being removed, or in plain language terms, it's like uranium, sulfate, arsenic, nitrate, selenium, nitrite, and chloride. So this is coming from a study done by Clifford in 1999. So you have the reference available, and it's also mentioned inside the design manual. So in here, you can tell for a strong base anionic exchange resin, if you're using it to treat for nitrates, looking at this, the resin itself actually much prefer sulfate over nitrate. So as the resin gets filled up and there's no more space, the sulfate will start bumping off nitrate, just like the previous graphic that I was showing. So this is a critical point for you to look at as you review. Right before regeneration of ion exchange resin, it's the nitrate bumping or dumping that's occurring because it can actually have effluent concentration higher than the influent. And not only you already have a health risk, that's why you're treating for nitrate, you can actually make it worse by having really high level of nitrate coming off. So that's called, the technical term is chromatographical peaking. It is due to the selectivity of the resin. A more preferred anion can bump off less preferred anion. The effect is called the peaking, chromatographic peaking of less preferred ion. It causes the less preferred ion to exit the resin bed at a higher concentration. This occurs if the bed is not regenerated at the proper time for the contaminant of concern. The effects of chromatographic peaking and it can also actually cause low pH, sometimes in the anion exchange water. But this can be minimized actually if for a system that may be having multiple columns that is operating in offset cycle. So maybe you have one column that is peaking while the other ones are operating properly, so that they will balance it out and able to keep the treated water below the MCL. So the chromatographic peaking is a concern in parallel beds and can be operated out of phase, as I mentioned. So the timing for regeneration and resin selections are critical. So here's kind of like just to show what I've explained before, like you have water coming from top to the bottom. On the bottom, you have fresh resin, and as you have the water coming in, the layer of preference will come here. So you have nitrate followed by arsenic followed by sulfate. Those will be the mass transfer zone of those water as it pushes down. So it is really important for you to, once the nitrate gets you close to the bottom of fresh resin, it's probably time to regenerate, and you don't want to wait so long so that the sulfates start filling up the column and then pushing off all the nitrate. So with standard strong base anion exchange resin, nitrate peaking is definitely possible. The nitrate concentration will be greater than and in the influent, and it's because the preference of sulfate over nitrate. But nowadays, actually, if you're doing nitrate treatment, be sure to look for there's some nitrate selective resin is now available, and it pretty much eliminates the concern for nitrate peaking, because on how they manufacture resin, they're able to make the resin to prevent nitrate over sulfate. So this nitrate peaking does not occur. So for nitrate treatment, it is possible to have select the nitrate selective resin to prevent that from happening. So it gives a little bit more room. So it'll come off more like a traditional breakthrough. Instead of being dumped, nitrate being dumped, it's going to stay at a low level and then start to rise. So maybe it'll be easier to operate for a smaller system. So the potential causes, so like this is kind of like for you to start troubleshooting. And if a water systems report to you that they're having difficulty with their ion exchange treatment, one of the potential causes is actually what we see in the most system. If they just simply did not put in the salt. There's no salt in the brine tank, or they just dump salt the day before you get there. So that's why the samples, the resin was not properly regenerated, and you grab a sample and the level is the same as the influent concentration because there's no salt. Or sometimes there could be a salt bridge in the brine tank. That's kind of like salt that you have dumped on top. The ones on the bottom has all eroded away, but it still looks full, so the operator is not adding salt. So there's a salt bridge, and the water and everything is under. So one good way to do it is actually for the operator to kind of like use a broomstick or something to measure the depth of the tank, and then being able to poke through it just to make sure that there's not a salt bridge. Or simply that they're regenerating based on the timer and they're regenerating too late, so that's why they have a problem. And also for sometimes you can look into the flow conditions of the ion exchange resin itself. It could be because there's a damaged distributor that is causing the system to be for the water to be channeling through the resin is not working well. Or they have over or undersized the system. When a system is oversized, you have too little water. That also promotes channeling. And if the system is undersized, the water is passing it through it too fast, so that maybe the ion exchange process is not able to complete before it comes off the other end. That will be having excess water flow rate. And then last but not least, also during the backwash, sometimes if you backwash so hard, it can damage the resin and actually can potentially damage the screen and push the resin out of it too. So all of these things are for you to consider if you're helping a water system troubleshoot what type of problem they're having. Another thing that for consider when you have bad performance is violence and irreversible damage to the resin. For example, there could be high iron or manganese or silica in the raw water. The iron and manganese can coat the resin and pretty much take away the exchange sites. So can total organic carbon. The organic matter can bind to it. Or you have a bacteria that's growing biofilm on the outside of the resin that's preventing taking away some of the ion exchange sites. Most importantly, there are some things that could damage the resin permanently, and you can reverse it. One of the things is strong oxidants, such as chlorine, chlorine dioxide, chloramines, ozone. If the water system have any type of chlorine treatment, it's probably most preferred for you to move the chlorine process downstream of the ion exchange resin, so you won't have the strong oxidant that can irreversibly damage the resin. So the disinfection should be downstream. Pre-chlorinated water should be used to prepare brine solution. And then so for point of entry applications, pre-treatment to remove the chlorine residual may be necessary. So this will be something good to talk to your the resin manufacturer to see if it's a problem. I think I may have a typo here on the pre-chlorinated. It should actually say non-chlorinated water should be used to prepare the brine solution, just to minimize the risk of exposing chlorinated water to. So I need to have a typo over there. And then also for some of the wells, if they have vertical turbine pump, there may be oil or greases that get pushed into the ion exchange bed, and that's really difficult to clean, as with anything else. Even when the water system is getting resin, it's important that they stay wet. If an ion exchange resin has dried out, it actually is damaged, and you won't be able to bring it back. And then also even for temperature, for those of you in really cold climates, really high temperature or really low temperature can also damage the resin. So all of these, check with the resin manufacturer to see the temperature range, what's the appropriate resin to use, so that you're using the correct one. And especially a lot of this resin will be sitting in a tank, could be off during the day, like in Bakersfield or something in California. The high temperature can potentially damage the resin as well. So for nitrate treatment, I'm going to call attention to that a little bit. Things to consider, because nitrate poses an acute health risk to customers. Water systems should generally use nitrate selective ion exchange media unless they really know what they're doing. There needs to be an adequate safety factor, and safeguards should be incorporated in the design. And every state, probably you guys have your own perspective on how much of a safety factor. Many of the small water systems do not have treated water storage in California, so the water goes straight into the distribution system, and there's no tank for you to blend out any of those nitrate dumping or any of those effects. Because of that, in California, we recommend or require a lot of systems to have online UV-based nitrate analyzer, but they are very, very expensive. They're closer to around $20,000 each for the nitrate analyzer. But that allows the system to be able to treat the water and run all the operation from regeneration to their blending operation, all based on the UV analyzer, so they can minimize the volume of waste. So in California, treatment plant effluent targets typically around 7 or 8 milligrams per liter nitrate as nitrogen, and this is achieved through both the ion exchange process. They have parallel columns, and then also through bypassing. So special considerations. Now I'm going to bring up like single pass systems. A lot of you probably will see more of this, especially with the use for PFAS treatment. The single pass ion exchange system, and it has no capability of on-site regeneration. Because of that, the resin could be working on-site for like 3, 6 months, 9 months, for a long time. It's a really attractive option for chemicals with high treatment capacity, and maybe used for radiological chemicals because it's very high selectivity. If you look at the previous slide, it is one of the most preferred for uranium. So no matter how hard, it's not going to come off of the resin. A lot of interest has been for PFAS because it has a faster kinetics than GAC, so which means it works faster, so you can have a smaller footprint than GAC, and has really high treatment capacity. But at the end of it, when you have all the loaded resin, you need to take it off all the way for incineration or for disposal. And then for radiological chemical treatment, just keep in mind that if they keep the resin in use for so long that there is a potential for becoming what they call a T-norm, or technologically enhanced naturally occurring material, because it absorbs so much radiologically active materials that now is radioactive, and you need to dispose of it differently. So typically, if you change it out, and manufacturers' resins, they have really good models. So if you give them the raw water condition, they'll be able to calculate for you how long the resin can last before it becomes T-norm. So you can change it out before you get to that point. It's a really good resource. So new systems. So when you're looking at brand new system, especially both for single pass system and for regular system, fines and silts is actually, for a lot of groundwater well, is your biggest enemy, because the fines and silt can really block water flowing through the resin and then cause channeling. When you're looking at system, really see if there's a water hammering issue, because the water hammer, as Mike mentioned earlier, even for membranes, any water hammer can damage filters. It can crack the under drain and then cause the resin to flow through the system, and you cause a lot of problem. So you want to see if there's a capability for you to have a more gentler start and stop. Pre-treatment for the well with sanding issues is critical. So you have some wells, like right now, they have no treatment, all the sand just get in the system, and you just flush it out once in a while to get rid of it. But now just think of that, this is like an amazing sand trap in the resin. It's just going to clog it, and you won't be able to get it out. Resin trap downstream of an ion exchange system is recommended to prevent resin from entering the distribution system. Just in case that you have a failure, you'll be able to catch it before it gets into the system. And then for a single pass system, a 5-micron pre-treatment cartridge is strongly recommended because of the long service life of the resin, especially it's going to be running for a year or longer. You have so much particles, and the 5-micron cartridge is cheap, so that you'll be able to change those out. And even maybe as a start, as your pilot testing, install a 5-micron cartridge just to see how much dirt you're capturing it, because all that dirt will come onto the filter and clog it. And then potentially include piping for on-site backflush is desirable, because like sometimes even with the perfect system, you can get some dirt and silt. If you have piping and hookups available for you to gently reverse the flow and get rid of the buildups of the sand and silt on top of it, that will be a really good ability. So I think the rest of this is kind of like I have some pictures. So this is just to show you a larger scale ion exchange system, not the softener side. They just have really big vessels like this. This is at a water systems in California, and they have 4 vessels here, and then they operate in off sequence. And then this is their jumbo-sized brine tank that they're able to blow the salt in. The stainless steel pipe is where they put in the salt, and then they have the water there to make it into the concentrated salt solution. And then these are the cartridge filters that they have, the jumbo size, for them to take out the sand and silt that's going into the system. And then these are some pictures from Purolite for you to kind of like look at like what the ion exchange resin. So these are like tiny little beads, and for the scale, so that you understand, looking at it, this is the top of a pinhead right here on the right, and you can see like it can easily fit like 8 little tiny little beads, and that's how small the ion exchange resin. So that's why these are really good at capturing silts and dirt particles and everything, and the critical part of the pre-filter. Otherwise, all of it will be trapped into resin. So to wrap it up, the takeaway for you, when you go into the sanitary survey for an ion exchange system, ask yourself these questions so you can prepare for it. What is the chemical being treated by the ion exchange resin? And then what is the specific ion exchange resins being used, like especially if they're doing nitrates, so that you can look up or ask the manufacturer, like, what is the sequence? Do I need to be concerned about any of the chemicals that maybe there are multiple chemicals in the water that could be bumped off? Has the influent water quality changed? Has the nitrate concentration creeped up, so that maybe that the regeneration based on volume treated is no longer conservative, and there's a significant amount of time that you may be sending water that's over the MCL target into the distribution system? What is the trigger for regeneration? Is it the old school based on time, or is it the newer one based on volume treated, or better yet, on an online analyzer that I've talked about? What is used for regeneration? Is it like potassium chloride, sodium chloride? It really shouldn't impact, but just so that you know. And are they using drinking water quality salts? That's state dependent. But they are widely available, the sodium chloride, especially even at a lot of the home improvement stores. When you look at it, they are certified drinking water additive. How often is the treated water sample? Like maybe they collect it once a month, but they just keep on missing the part that you have a lot of time that's over the MCL. Is the treated water served directly into the distribution system, or is there a storage tank prior to distribution system to give you a little bit of blending in case there are some breakthroughs? Has the ion exchange resin been changed? Talking to the operator, find out if there's like any resin loss. Like they say, oh yeah, we topped it off or something like that. That may be a signal that they have a failed under drain system or something, or they're backwashing too hard, because the resin should really stay put and not be lost. And then this is something that I would suggest for you when you go out for your inspections, is prior to visit, really, if you have a good database, be able to look at the raw water quality database, look at when the system was put in and what is now. Has the level increased since the original design, so that you have an idea of when you ask the question. Determine how system regeneration works. Have to read up on it, understand, and is it by time? What's the process? Does it go through the rinse process? Review any available treated water data to see how well they're doing. Is the treated water consistently and reliably below the MCL, all samples, or depends on the state? Is it on a running annual average basis? Like I think as a treatment operation, you want all samples to be below the MCL, but compliance is based on the running annual average except for nitrate. And then request the public system to collect a treatment plant effluent sample prior to storage tank, just before regeneration, before your visit. So this is kind of like one of those telltale samples. Like just work with the operator, like, hey, next time before the system regenerates, just grab me a treated water sample and run it to the lab. Just want to see if that sample is over the MCL or not, so that you know exactly where it is in the breakthrough curve. And that this is an ongoing special sampling that we recommend in California for water systems to collect annual just before regeneration samples, so that they can check just to make sure how the treatment system is working. Is it degrading? Is the breakthrough occurring before the end of the treatment? And then a breakthrough curve can actually be developed by collecting periodic samples along the volume treated, so that they can really capture how the system is working. So I think that's the end of my section. So we can move on to the poll questions, please.
Okay, great. The first poll has been launched. It is ion exchange resin media can only be used once and must be thrown away when it reaches treatment capacity. True or false? And it looks like we had 77% say false.
Sounds good. 77% of you got the correct answer, because there are some ion exchange resin that can be regenerated, but as I mentioned, like for PFAS treatment, a lot of those are single pass treatment, so they have to be thrown away after single use, or they could potentially be regenerated off-site and then used for for site cleanup or something like that. We don't recommend that for drinking water. Next questions, please.
The next poll has been launched. It is another true or false, and it's I can use the same ion exchange resin that is used in a water softener for treating nitrate or arsenic. And we had 63% say false.
That is correct. So false is the correct answer. The ion exchange resin really makes the difference, because you're using the same brine solution. So it is the resin itself that's able to tell you whether you're removing positively charged ions like calcium and magnesium, or negative charged ions like nitrate and arsenate from the drinking water. So it is critical for you to use the correct resin for your target contaminant. Next question, please.
Okay, we have another true or false, and it is I can use the same salt or sodium chloride, potassium chloride that I purchase at a home improvement stores for treating nitrate. And we had, so a little closer, we had 51% say false and 49% say true.
Okay, so I did informal, I'm not advertising for these companies, so I went to 2 home improvement stores to look at their water softener salt yesterday. And both of them, they are labeled NSF 60 for drinking water treatment. So if you are able to find salts, and depends on your state, right? If your state requires NSF NC 60 for drinking water additive to regenerate resin, and they are available at the home improvement stores, just looking at it, they can take a picture of it. I went to the 2 big brands, the orange one and the blue one. Both of them have NSF 60 salt available. So I think, so the answer is yes, you can use regular water softener salt for treating nitrates if you're using for ion exchange resin regeneration. Thank you.
Okay, we have 2 more polls. This next one is using strong base AIX to treat nitrate. What is the phenomenon when the effluent concentration is higher than the influent concentration? Please select one. Okay, and we had 44% say all of the above.
Yes, so 44, the 44% got the right answer. So I was having a little bit of fun with the question, but yes, it's all of those are the correct terms, and there's probably you need to issue a tier 1 public notification because they're serving nitrate over the MCL. So thank you.
All right, and the last poll is a groundwater well is contaminated by total coliform. Following well disinfection with chlorine, what should I do next? And for this question, we will assume that the well has a residual of 2 milligrams per liter of free chlorine. And for this one, we had 63% say B and C.
That is correct. That's the right answer. Take advantage of a lot of the ion exchange resin, especially the company, the sales department, they have really good technical support, or they can put you in touch with the technical support. So whenever you have a problem with a resin and how to restore performance, take advantage of it. So like in this case, you can really disinfect it. And if the well is contaminated and then now you have coliform positive, they'll be able to give you advice of what to do, or maybe having extended regeneration cycle for you to disinfect the resin using a high brine salt solution or something like that. So that's why B and C. It's important for you to avoid the high chlorine going to the system, but check with the resin manufacturer. They'll be able to tell you how tolerant the resin is, and it's kind of like using the CT concept, how much chlorine and how much time you can expose to it without permanent damage, but they will be able to give you good advice. So B and C is the right answer. Thank you.
Great, thank you. And those are the polls for your section. And next we will switch over to Karen.
Great, thank you very much.
Hi, everyone. Mackenzie, can you hear me all right?
Yes.
I'm just going to say hello, and then I'm going to go off camera. So I wanted to say hello, and now I'll put on my presentation and turn me off. How does that look?
Don't see them yet. 1 second. Okay, Karen, now could you accept that notification?
Yeah, hold on.
Great. Wonderful. Great. Looks good.
Good. All right, I'm going to talk to you today about UV pretty briefly, and considerations as you're conducting sanitary surveys of UV units and UV setups at a variety of sizes of water systems. So I think you've all seen this disclaimer before. I am going to trust that you read it when Mike was talking and move on. And give a bit of an overview about UV. So UV is an attractive option for many water systems because it really doesn't form disinfection byproducts. It can be very effective for inactivating cryptosporidium, and giardia. And unlike some other disinfectants, inactivation using UV doesn't depend on temperature or pH, which has some good applications. UV disinfection also doesn't change the pH or the corrosivity of the treated water the way you might see with some chemical disinfectants. The downside is some viruses, especially the adenoviruses, are more resistant to UV light than crypto and giardia and therefore require higher doses. EPA, as part of the LT2 Enhanced Surface Water Treatment Rule, published a table providing UV dosages that were required for different log inactivations of pathogenic microorganisms. And we'll talk about that. I'll show that table in a bit. A few other notes of caution about UV as we get rolling, and we'll talk about these things in more detail. Since UV is a physical disinfectant, it doesn't leave a residual in the water. So a secondary disinfectant usually has to be added to maintain a distribution system residual. High turbidity and organic matter in the water can shield organisms and prevent them from being exposed to UV light. So it's recommended that water systems apply UV light after filtration where the turbidity and organics in the water have been removed. You can have problems with scale. We'll talk more about that on the sleeves, the quartz sleeves that house the UV lamps. Any concerns with hardness, alkalinity, and pH. And for example, a hardness level greater than 120 milligrams per liter as calcium carbonate is a threshold of concern. We'll talk a little more about that as well. Two other things to note. You'll see that there's mercury gas in these UV lamps, and mercury can be released into the treated water if a UV lamp were to break. So the amount of mercury that could potentially enter the water depends on the type of lamp and its operation, but just be aware of that. And finally, the operation of UV lamps can be temperature dependent. Usually on the warm side, UV lamps are designed to operate within a specific temperature range to maximize the UV light output. And it's risky without flowing water moving through the lamps to cool them. The lamp temperature can rise above that maximum operating temperature and potentially break. So these are all sort of caveats walking into this about UV, but let's keep going. Talk some more about how UV works. So the way UV disinfects is the UV rays inactivate microorganisms by penetrating their cells and damaging their DNA, which interferes with their reproduction. UV light is the region of the electromagnetic spectrum that lies between X-rays and visible light, as you see here. That UV spectrum can be divided into 4 regions. Here they're listed as vacuum UV, UVC, UVB, and UVA. Really, the UV disinfection primarily occurs due to the germicidal action of the UVB and UVC light on microorganisms. Germicidal action of UVA light is really relatively small compared to UVB and UVC, and takes much longer exposure time. So UV lamps operate in much the same way as fluorescent lamps do. UV radiation that is emitted from electrons flowing through ionized mercury vapor produces the UV energy for most units. The difference between the two is that the fluorescent lamps have a phosphorus coating that converts the UV radiation to a visible light. There's no such coating on UV lamps, so it transmits UV radiation generated by that arc. Let me make sure. So a few ways that UV light interacts with materials in the water. The first is absorption. UV light's absorbed by particles in the water and by components of the UV reactor itself. And once that UV light is absorbed, it's no longer going to be disinfecting any microorganisms. So that's a key factor in terms of how UV light reacts with water. Three others, though, refraction, reflection, and scattering, are all different ways that light direction changes in the water, but that UV light is still available and still able to disinfect microorganisms. Some factors to know: UV absorbance measures the decrease in the amount of light that passes through the water over a specified distance or path length. And UV transmittance, which many of you are familiar with, is the percentage of light that passes through the water over a specified distance. All right, it's not going. There we go. UV intensity measures the amount of UV energy that actually penetrates the water that's being treated. But now UV dose is the amount of that UV energy that's penetrating the water multiplied by the amount of time the water is exposed to the energy. So it is the UV dose that's determining the amount of pathogen kill that you get. So it's both the intensity of the UV light and the exposure time. There are different arrangements for that UV dose to be delivered. I'm not going to go into them today because we have a lot to cover, but just know these are two of them: the continuous flow UV reactor and a completely mixed batch system. And that the way you figure out dose delivery depends on these arrangements. And for example, dose delivery in a continuous flow UV reactor is considerably more complex than it is for that completely mixed batch system. But that's all usually done before you're going out and looking at a UV unit as part of a sanitary survey. Now, we talked about the UV intensity and the UV dose, but then there's also the UV dose response. So how a microbe responds to UV light certainly varies among the various microorganisms and pathogens. The UV sensitivity of viruses and bacteriophages can vary by more than 2 orders of magnitude. UV dose response is determined by irradiating water samples that contain the microorganism. It's pretty straightforward. Doing that with various UV doses and measuring the concentration of infectious microorganisms before and after their exposure. That makes sense, right? But it does vary a lot, as many of us know. So one thing to be mindful of is that the UV dose response is independent of these things. UV intensity, the same level of inactivation is achieved with a given UV dose, regardless of whether that dose was obtained with a high UV intensity and low exposure time, or vice versa. UV absorbance of the suspension is considered when calculating UV dose. Increasing intensity or exposure time, however, may be necessary to achieve a constant UV dose, as the absorbance of a suspension will change. Temperature effects on dose response are really minimal. and they depend on the microorganism, but temperature generally does not affect the dose response of a particular microorganism. And finally, pH. The dose response is independent of the suspension's pH, of the water's pH, within the range of pH 6 to 9. So be aware of that. Because there isn't a I think my headset went out. Hopefully you can hear me. Certainly particle association and clumping of microorganisms will affect the UV dose response. You'll have shielding in a similar way that you might see with chlorination and other disinfectants. And know that the UV light at 260 nanometers is actually the most effective at inactivating microorganisms, but 254 has become the standard, primarily because that's what's emitted when you use mercury, and it's just the most efficient way to do it. Let's keep going. This is just at this point rather old graph that shows how varied the UV dose response curves can be among various pathogens. And you'll see that some react very quickly. E. coli reacts very quickly, whereas this doesn't really show the tougher viruses that may take a while longer, but it gives you some feel for how varied the UV dose response curves are. Let's talk a bit about the UV lamps themselves. Both low pressure and medium pressure lamps are available for UV disinfection applications. Low pressure lamps emit their maximum energy output at a wavelength of just shy of 254 nanometers, about 253.7, while medium pressure lamps emit energy with wavelengths ranging from 180 to 1,370 nanometers. The intensity of medium pressure lamps is much greater than that of low pressure lamps, and therefore fewer medium pressure lamps are needed for an equivalent dosage. For small systems, the medium pressure system may still consist of a single lamp, regardless of whether it's a medium or low. And typically, you'll have a quartz sleeve enclosing the low pressure lamps in order to separate the water from the lamp surface. This arrangement is required to maintain the lamp surface operating temperature near its optimum of about 40 degrees Celsius. So as I mentioned, lamps generally have an output, certainly the low pressure lamps have an output at 254 nanometers. One thing you have to be very aware of is how sensitive UV lamps can be to unreliable power sources. So any kind of voltage fluctuations, interruptions, even if brief interruptions of power can basically mess with the arc of the UV that is passing through the lamp. So you really want to avoid that. So many UV units are equipped with these ballasts that regulate the power supply and ensure that the power is consistently provided to the UV lamps. Ballasts usually operate at temperatures below 60 degrees Celsius to prevent premature failure, and therefore they usually generate enough heat that you need some kind of cooling fans or air conditioning around them to keep them in that range. So be mindful of that when you're going out and looking at a unit, that if you don't hear the fan running, it really should be running to keep the unit within that temperature range to be operating optimally. I skipped the second sub-bullet there because I wanted to take a moment to talk about startup times for lamps. And when you're going out and doing sanitary surveys, I think it's pretty important. Many of you have done sanitary surveys. So I was just at a water system where all of their chemical feed pumps are tied to the wells. So they kick on when the well kicks on. And that's great. but be mindful that there may be a startup time. There might be some lag time for UV lamps before they're fully operational and appropriately disinfecting. So that startup time for lamps should be considered when you're setting up the whole arrangement of what's kicking your UV lamps on and all that. Another important element to all of this is lamp age and the aging of lamps. So lamps degrade, both low pressure and medium pressure lamps. It's a function of the number of lamp hours that the lamps were in operation, how many times they turn on and off, a few other things. But know that the reduction, that you're going to have a less powerful UV light with time. And there are a few other things that sort of make it exacerbate this. Any deposits on the inner or outer surface of the lamp envelop any deposits on the inner or outer surfaces of the lamp or metallic impurities inside the envelope can absorb UV light and cause premature lamp aging. Also, if the lamps are not sufficiently cooled during operation, electrode material in the medium pressure lamps can evaporate and condense on the inside of the envelope. So you have to be aware that lamp age is very much a factor in operating them appropriately. I touched on this already, conditions that affect UV performance related to water quality. Certainly turbidity, high total suspended solids will interfere with the transmissions of the UV light. But also when you're going out and looking at a system, be mindful of upstream water treatment processes. There are a few that can really interfere with UV. One example, the big example is ozone. If you have any kind of ozone upstream before your UV treatment, it's a strong absorber of UV light, so you really don't want that ozone to be in any way in the water when it's passing through your UV units. You want to quench it before then if you can. But be aware that thiosulfate's not recommended as a quenching agent. It too absorbs UV light and can decrease the UV transmittance. A few other things also interfere. Some corrosion inhibitors absorb UV as well. So be mindful of that. And as I said, there's a high fouling potential. So especially hardness, iron, these all can interfere and foul up your lamp sleeves and your monitoring windows and really make the whole unit less effective. But at this, a lot of the units now have built-in cleaning equipment. You want to make sure all of that equipment is working properly when you're reviewing the system. All right, it's not letting me go to my next slide. Mackenzie?
Hey, Karen. Try clicking on the slide first and then using the arrow keys. That sometimes like resets it. If not, I can share your slides for you.
Oh.
There we go.
All right. How many do we go ahead? Just one. That's good. Okay, great. Okay, yeah, just a few things to be aware of about UV disinfection. You can see if you have chlorinated water or chloraminated water going through a UV unit. You can see a reduction in residual as a result of that. It's generally proportional to the dose that you have in the water and will be independent of flow rate. Things that don't impact it. So as water moves through a UV unit and then is disinfected, there's no really significant effect on the formation of the brominated or chlorinated DBPs, nor is there an increase in assimilable organic carbon at the lower UV doses, the way you might see after ozone. And converting nitrate to nitrite doesn't seem to be too significant an issue for water systems either. So I mentioned the dose table that is in LT2. I think it's also in a few other places, including the EPA's UV disinfection guidance manual. So this is this table here shows
Hey Karen, this is Mackenzie. You might be muted. Karen, can you hear me? Okay, one moment.
hello?
Hey Karen, I think you
Can
might
you
have been
hear me?
muted. Yep, now we can hear you.
I didn't do anything. I have a big sign that says it's not you, it's us.
Yeah, that was just because we were
It's-
having technical
yeah.
issues, but now I think we're all set. I will share your screen again.
Okay, thank you.
Mhm.
Yeah. Oh, it's doing it again. Oh, hold on. Mackenzie,
Mhm.
which screen do you see right now? I'm sorry about this.
I
Do you
just
see
see a
the
blank
smaller one?
screen right now.
Oh,
Let me share your
it's
screen one
not.
more time.
Oh, hold on.
Oh, there we go. Perfect.
Are we
All
good?
set. Yep.
I'm
Great.
sorry, everybody. Hopefully you can all hear me. Where were we? um, I'll just keep going. So the UV dose does depend, as we said, it depends on UV intensity as it's measured by UV sensors in the unit. Also the flow, how fast the water is moving through the unit, and UV transmittance. So how effectively the UV light is transmitting through the water itself. And this is the table of dose requirements for LT2 that's in the UV disinfection guidance manual. And what I was pointing out, and I don't know if you heard me or not, is just if you take a look, is to show how incredibly different the millijoules per centimeter squared, what's required for 2-log inactivation of crypto and giardia as opposed to viruses is. You really see it here. And just to clarify, this is water, no pun intended. This is water that's post-filter for filtered systems or is meeting the filtration avoidance requirements for the unfiltered systems. And just know that LT2 has several requirements related to the use of UV disinfection as a microbial toolbox tool. They address UV dose for different levels of inactivation credit, performance validation testing of the UV reactors, monitoring, reporting, and off-specification operation. Let's talk just for a minute about validation testing. As I said, it's required by LT2. because there are uncertainties as you are installing UV units at different water systems. So water quality, the hydraulics, enough things that UV reactors undergo validation testing to determine what operating conditions under which the reactor should deliver the dose that's required for the necessary inactivation levels. In general, operating conditions determined in validations testing should include flow rate, UV intensity as measured by a UV sensor, and UV lamp status. These monitoring and operating conditions would both be a part of a primacy agency approval of an alternative treatment process and associated compliance monitoring. So when you're going out and doing the sanitary survey, this should have already been established as part of the plan review and approval process for the UV unit. But your job during the sanitary survey is to confirm that they are in fact operating their unit according to within the parameters that were established as part of the validation testing. Another requirement for LT2 is that both filtered and unfiltered public water systems have to treat at least 95% of the water they deliver to the public each month by those UV reactors within, they have to be operating within validated conditions for that required UV dose. So really they should try to do it all the time, but the minimum is at least 95% of the time that water, not of the time, 95% of the water that is delivered has to be produced under those validated conditions. So what you'll see if you're doing a sanitary survey, usually I think most states have a pretty good monthly operations reports forms that capture this information, and they can be reviewed as part of the survey. So there's that initial reporting that says what the validation test results are and the operating conditions that need to be complied with. And then there's the routine reporting that is the operational compliance monitoring. So the percentage of water entering the distribution system that was not treated by UV reactors, among other things. Lamp age, you'll see on a operations report, you'll see lamp age, you'll see flow for sure, and other things that are basically establishing that they are meeting the parameters, they're working within the range of parameters that were established during the validation test. Along those lines, the public water systems have to demonstrate that they're operating within that approved range of conditions. So usually you'll see information about flow, lamp status, which might be really primarily is lamp age, UV intensity is measured by the sensors, and any other parameters that are required by the states. There also are requirements on public water systems to calibrate their sensors according to a protocol that's approved by the state. I would like to add that this is a small system workshop. I've seen several really small UV setups where they don't have a flow meter on them, and instead they'll have some kind of a flow restrictor built in so that they never can exceed the allowable flow rate. Just other things to look for at a UV unit that to be aware of is that they may have sensors that detect a quick drop in UV lamp output intensity. Certainly alarms and shutdowns. Do they have a solenoid that shuts them down if they drop below, say, 70% transmittance? Or is it an audible alarm? If it's an audible alarm, make sure it's not in the basement and nobody's going to hear it. Is it tied into their SCADA, things like that. There are also automatic or manual cleaning cycles built in. There's sleeve cleaning brushes and equipment built in at this point for these units. And be aware that some systems are being operated remotely, so they may have a telemetry component to them. So when you're looking at the smallest of the UV units, look for these things. Look for their intensity meter. Talk to the operator. What are they looking for in terms of a minimum intensity? In minimum percent transmittance, which is different. But make sure that they have some sort of a shutoff if they are required to be producing water that has that kind of disinfection. If there are any requirements on water quality coming into the UV unit, do they have a way to sample that with a raw and finished water tap? Do they have any kind of cartridge filters up front or other filters up front? If it's a groundwater system where you may have some concerns with some suspended solids or turbidity. I mentioned the flow restrictor. Do they have spare bulbs on site so they can replace them should they go out? Keep an eye out for bypasses of UV units. Every state has their own requirements, but be mindful that they are out there. Some people don't like those automatic shutoffs. So some questions and considerations as you're doing your sanitary survey. Are they meeting their dose and inactivation requirements? If they have to do the 95% threshold of the LT2, are they delivering that water that's at least 95%? If they are not, as part of the sanitary survey, you really should review those periods where the system was operating outside of the validated conditions or off spec, and what caused that to happen. Try to review what changes the operator has made to try to respond to that as well. You should be confirming that the system is verifying its UV sensor calibration and recalibrating consistent with your state's approval protocol. Also confirm that a reference UV sensor is present and operating. You should verify regular maintenance of the UV and flow monitoring equipment and procedures for testing critical alarms to make sure that they in fact are working and what they do, that they're very responsive to it. So maintenance procedures include cleaning the UV sleeves, maintaining sleeve cleaning equipment, UV transmittance analyzer cleaning and maintenance, and the maintenance of the ballast cooling systems, water level indicators and thermometers. You should review the performance of the treatment processes upstream of UV disinfection. I'm worried that I cut out again. I apologize. You should review the performance of treatment processes upstream of UV disinfection that could have an impact on your UV's effectiveness. These include turbidity reduction, iron removal, softening, and make sure that during the survey, make sure that there haven't been any changes to these things. You know, how things are, the hydraulics of the plant impacts the upstream treatment might have. And that they hadn't, I think Mike Finn touched on this with the membranes. Just make sure they're not using different UV lamps or sensor make models that don't match what they've been approved for. And then finally, just check that there haven't been any changes in the source water. Water quality is really key to effective UV transmittance. So are they using any new sources? Have there been any sort of really big spikes in turbidity or changes in the quality of the water that might impact the amount that you get a scale buildup or you're concerned about turbidity coming in. And I think that's it for me. I apologize for my audio issues. Hopefully everybody heard that.
Yep, great. And we have 3 polls for you. Can do those now.
Right. Do I have to do anything,
Nope,
Mackenzie, or you
nope, you're
just?
good. Yeah, the first one has been launched.
Okay, great.
So the question is, UV dose is the product of, and then please select your answer from those below.
So I don't see the poll. Oh, I have to go on the side, right?
Mhm. Great. So it looks like we had 71% say intensity and exposure time.
Absolutely. So remember, intensity measures the amount of UV energy actually penetrating the water that's being treated, and dose is the amount of that UV energy multiplied by the amount of time that the water is exposed to that energy. So correct. Great.
Great. And the next one has been launched. It is, which of these conditions is not likely to reduce the performance of a UV reactor? Please select your answer below. Great. And it looks like we had 92% say cold water temperature.
They're all over it. Yeah, absolutely. Cold water. That's what's one good thing about UV is that it, unlike chlorine, you don't have to worry about various water temperatures in terms of the effectiveness of the UV. I mean, especially the cold water, where that becomes more of an issue for the chemical disinfectants. Correct.
Wonderful. And the last one has been launched. And the question is, which of these should be considered more closely if you see it during a sanitary survey? Please select your answer. Great. And we had 93% say all of the above.
They're all over it. Yeah, absolutely. Yeah, all of these things should be considerations when you're checking the system. Excellent.
Wonderful. Great. And now we will switch to Mike for his presentation.
Do I need to stop sharing?
Nope, you're good. I'll
Okay.
make Mike the
Thank
presenter
you.
now. Thank you, Karen.
All right, the mouse is not cooperating. What's the deal here?
I think if you just go up to slideshow up top.
Yeah, I'm just not seeing, I don't see my mouse, I mean my cursor for some reason.
That's what I had, Mike.
There it is.
Do you have?
It
Yeah.
is. All right. Okay. Okay. We were asked when we started this workshop to cover some things. Again, as I said, that some folks may not see it very often or have not seen before. Ozone in particular is one that we were asked about to talk about. It's not necessarily a small system technology, although one person's small system is another person's large water system. So this is, again, to cover some things in detail that we don't usually get to cover. This one in particular, we do this really quickly in a sanitary survey training and I get questions about it. So, all right, here's our disclaimer that you've seen many, many times. All right, ozone disinfection. It is a chemical disinfectant. It's just formed differently, that's all. So it's generated as a gas on site using an ozone generator and either dried air or liquid oxygen. And then it's ejected, like other chemical disinfectants, into the pipe or an ozone contact chamber, which we'll talk about. It is operated, the whole system is operated under pressure. Ozone will, off gas will volatilize. So and if you're trying to get disinfection, almost always, there's a few exceptions, which we'll talk about. The entire system is under pressure. Very effective disinfectant for viruses and Giardia. Very low doses, contact time is low, much lower than chlorine, but something we kind of discovered or was looked at after long-term 2 was established is that the doses needed for cryptosporidium are relatively high. So systems that had ozone in place sometimes had to look for other options to deal with any cryptosporidium removal requirements to get it back there. Right, too fast. So what does it do? It's got a lot of pluses. It's very effective at reducing precursors. Very often used for that alone, just removing organic matter. It'll oxidize iron and manganese, taste and odor compounds. As I mentioned, it will oxidize TOC. For the upcoming contaminants, it will oxidize cyanotoxins, and it will oxidize synthetics like pesticides. So very effective, especially as a pre-treatment. And as I mentioned, here's kind of the comparisons between effectiveness of disinfection. If you look here, while the ozone doses are some cases an order of magnitude lower in terms of viruses, E. coli. You can look at the Giardia. That's a pretty huge difference. And then even though it's not necessarily effective against cryptosporidium, it's a lot more effective than free chlorine. So how do we make ozone? Kind of the same way that ozone gets made in the atmosphere. Your liquid oxygen or oxygen is passed across the dielectric, high voltage, and then ozone or oxygen is converted to ozone. So, and here's some photographs, just an example though, if you've never seen one, that is an ozone generator. Those are the dielectric, the tubes that are inside the reactor, which you can see on the right-hand side where the tubes are inserted, water flowing around the tubes, exposed to the light and changing, converting oxygen to ozone. And that's just an end view of what that it's kind of hidden here by the racks. Those, by the way, you can actually, if you look close enough, you can see a color difference there. So on your right-hand side, which is important, those tubes have been cleaned versus the rack to the left, where you can see some oxidation, fouling of the tubes. All right, so again, the value is it usually does not result in DBP formation, except for bromate. If bromide is present in the source water, it is the case in some parts of the U.S. It is a case in some groundwaters in the U.S. where there's bromide present. As most of you may know, there is a requirement for monitoring for the systems using ozone for bromide, I should say. However, no residual, right? Off gases, comes out of solution. Dissolved ozone will come out of solution, will volatilize. System is operated under pressure, so does not produce a residual. Like other chemical disinfectants, efficacy is affected by turbidity. Organic matter obviously absorbs it. Water temperature has some effect on how it's dissolved, but it's fairly pH independent. But as I mentioned, not necessarily small system technology, specialized equipment and construction materials, very high energy use, stainless steel used in most of the piping, very expensive to put together. So what do we use it for? It can be used in basically before filtration, after filtration, and as final disinfection. Before filtration, pre-oxidation. You're reducing NOM, natural organic matter, so reducing precursors, oxidizing taste and odor, causing compounds, volatile compounds, the synthetics. Can be used before biological filtration to improve removal of DB precursors. And phrase that differently, the biological filtration generally is needed both for precursor removal and assimilable organic carbon, which is formed in ozone. In the next bullet, as mentioned, AOC is formed, can be formed as the ozone is breaking down the TOC, and that AOC is great food for microbes to grow. So usually a biological filtration process is needed to get some of the AOC out. Inactivation credits. Ozone demand may be too high to generate a residual. In a lot of cases, the raw water quality is such that the operation isn't able to generate an ozone residual at the end of the contact basin. So in that case, there's what people call the automatic credit, which is a half a log GRD inactivation if the utility can measure 0.2 of a part to leaving the contactor exit. Can be used intermediate between sedimentation, flocculation, and filtration. Used before filtration, as I mentioned, removing DBPs, precursors, and then filtration, removing AOC. The inactivation credits lower demand from the oxidation process allows a higher residual. So low doses produce significant inactivation except for cryptosporidium. And finally, the final, filtered water ozonation. You have a lower demand, obviously, of the filtered water since you removed solids, you removed a lot of the organic matter. And again, very low doses and under that circumstances provide significant inactivation except, again, for cryptosporidium. The ozone doses needed for cryptosporidium are very high. I think we found in developing LT2 that existing contactors, those that have been built before then, may not be able to achieve any significant inactivation. And obviously, if you're meeting a whole bunch of your inactivation with the ozone, you don't need as much chlorine. However, you're getting finishing the inactivation. Taste and odor reduction are pretty significant versus the other chemical disinfectants. And as I mentioned, really no such thing as an ozone residual under the distribution system. It comes out of solution under atmospheric conditions. And ozone is a pretty strong oxidant, can damage a lot of things. As with other chemicals, we may need to, I think Karen mentioned it, you may need, depending on the downstream process, they may need to quench any residual before it sees any other unit process. So I think we touched on this, pretty significant reduction in natural organic matter, but you're forming assimilable organic carbon that is really good food for things to grow. Generally, biological filtration is used to reduce the AOC, but those of you that dealt with biological filtration in water treatment plants know that some operators don't like it, or they just need to pay a lot more attention to filters and how they're cleaned, how they're maintained when they let the filters go, what they call go biological. And then it does form bromate, and there's a compliance monitoring requirement that goes along with that. And I mentioned the need to quench the residual if necessary, because it will react, in particular, will react with chlorine and chlorine dioxide and reduce those. It will form chlorate with chlorine dioxide. Chlorate is not yet regulated, although I believe it's regulated in California, I believe. And then it is a pretty strong oxidant, like I mentioned. It'll damage pretty much anything except stainless steel, which is what's used. And then, the ambient air monitoring for worker safety and others is needed. All right, a couple of examples here of how ozone is used and how it's added to a water supply. The top left diagram, pretty typical ozone contactor where ozone is being fed in the distillate in the chamber, first chamber, up water flowing through the serpentine basin, and out the side with the addition in the first two cells, and then your contact in the reactive cells in the, to your right. A couple other examples. These are just configurations of the same thing. Either way, you're adding ozone into a cell and you're circulating water through a serpentine to get the contact time. Ozone can be added directly in a pipe, and sometimes it is. In that case, you're adding ozone, it's dissolving in the pipe, and you're measuring at the end of the pipe. The residual and contact time is in plug flow from one end of the pipe to the other. These last two, these are open channel ozone, which don't usually get used for a lot of reasons you're probably aware or can think of why they don't usually. Open channel is not usually used in public potable water treatment. And this is just, I won't go through this. This is, you can see in the long-term 2 toolbox guidance manual, there's really a lot of information about what, how ozone is added and measured. I just added this for completeness, what some common terms are. I mentioned that, the first one we're adding ozone is a dissolution chamber. There's a reactive chambers that follow that. Configurations might vary, but, and then, as you can see, the flow is countercurrent, flows up and around the basins. In this case, there's a second dissolution chamber, and then an extended zone, which I won't get into, but they're consecutive reactive chambers with ozone residual measured at the outlet. So here's an example that may look familiar from others, how ozone CT is done. And the important point about this is where ozone is measured. As you can see, it's being added as a dissolved gas. So where the residual measurement is taking place is important. So the demand, just like in other systems, the demand should be met. So in this case, we're measuring the outlet of number 1, and we're measuring the outlet of number 2, and we're measuring the outlet of number 3, and then measuring the outlet of number 4. There's no residual left, which in some cases is how systems prefer to operate because they don't want to see the ozone residual on other things. So they work at just meeting demand and just meeting their CT requirements. So the numbers here, I'm using the conservative T10 method that's in the guidance manual if you want to spend more time on it. General recommendation, general guidance is that no credit for the first chamber, because that's a dissolution chamber. Chamber 2 is just like you'd measure in any other reactor. It's either CN, concentration in, concentration out, or divided by 2, or just measuring the concentration out. Similarly for the next one, concentration out divided by 2, and then chamber 4. There are different ways to calculate it, but I'll just leave it at the first one for simplicity in our example here. So here's the numbers. I think they're in the previous slide. Yeah, they're using CNC out because that gives them a higher residual. The next chamber, they're using the measured C out, and then chamber 4, the concentration is 0, leaving the reactor. So assuming, really important, we won't talk in detail, but really there's only 2 ways to determine CT in an ozone contactor. It's either to use a conservative method with a tracer, as you would in any other basin, or there's some other extended methods that I won't talk about that would take a long time. So in this case, we're assuming all the chambers are the same size, same contact time. The tracer test gave us a 0.6 ratio, so we're using that short circuiting factor for all of the chambers. Again, chamber 1, no credit, it's a dissolution chamber, and then we add up the concentrations for the next 2, and then lastly, there's no residual leaving chamber 4, so that's a 0. We sum up the CT in each chamber using water temperature, and then that formula. There are tables as well. That formula is also in the guidance manual, and we come up with that's about a half a log of inactivation for cryptosporidium. As I mentioned, it's the cryptosporidium in particular is tougher for ozone to deal with. All right. And then I mentioned, I'll just, for example, if you're not using a T10 concept, if you're not using a tracer test, I won't spend a lot of time, but there's a decay rate determination using fluid mechanics, kinetics that can be used to determine what's called a K factor, and rather than use a tracer test, and it can be used, it's programmed automatically. There's some really good information in the guidance manual if you want to look it up. So what questions do we want to ask? What is the inactivation target? As I mentioned, it's really different for cryptosporidium, sticks out. Where is it measured? For contactors, generally the sample ports should be places where they do not affect the readings. I mentioned that wherever the analyzer is, if it's getting ozone that hasn't dissolved yet, it's the readings are higher than it should be. And again, in a pipeline, simple like any other pipeline, C is measured at the point of CT determination. And then there are lots of methods being used for this. Important question to ask. Some of the methods I mentioned, the extended zone up there, are fairly complicated, and it may be programmed into a SCADA, and it may or may not be, the operator may or may not really know how it's being done. And what are you looking at? Reviewing an ozone system, tracer tests, important. If they're going to use those methods, as you do in chlorine and others, and a tracer test, did anybody actually look at the tracer test and approve it? Or are they just using something that they develop on their own? For the decay rate methods, I mentioned there is a study needed, usually at least 3 months, and they're determining the decay coefficient of the ozone. It's a fairly specialized study. Are there any other operating conditions that would affect inactivation? Water temperature, raw water turbidity is important. It will make significant demand on the ozone. It's oxidizing a lot. And then plant flows through the reactor, just like the UV system we talked about. Plant flows through a contact chamber, any of those. And then how often do they do the determination, and how do they do the calculation? In order to do that, they've got to measure ozone residual, and there's 2 methods. I won't spend a lot of time. The first one is in standard methods if you want to look it up. Actually, they both are. Indigo trisulfate, they're using a colorimetric method, taking a grab sample, taking it to the bench, and getting an ozone residual. And then you're comparing that grab sample against the method blank, like any other benchtop analyzer. Amphometric probes, they use a semi-permeable membrane that allows ozone to basically pass through it, and they can be used quote unquote in line, so they can be located directly in the contact basin. In order to use some of these methods, extended one, as I mentioned, you need multiple probes, multiple reactors. So what else? Are they taking operational samples, and how often? Is it every shift? Does the operator actually write it down someplace, or are they just handing off? You obviously need reagents for any analytical methods, SOPs, just like you had in any other treatment plant for calibration of the bench analyzers and the probes. And then if they're using sensors, verifying those sensors with a grab sample. So as I mentioned, the sample port location is critical. You need to be measuring dissolved ozone entering or leaving the chamber. If it's not dissolved yet, that's not an accurate measurement. Detention time and sample piping, whether using probes, should be minimized to get an accurate measurement. If they're using multiple methods, which one are they using for your compliance determination? You shouldn't be picking and choosing. And it should be a method that you actually look through, and they've identified in their operations plan, for example. And when is it made? When is that determination made? Is it startup? Is it max flow through the day? An ozone chamber, it's kind of like UV does. You can't really start and stop it. The ozone generators have to start operating, get pressurized, start adding pressure to the system. Startup and stop is not really optimal, and most of the time they're left running, but it's not a start and stop like adding chlorine. And then overall reliability. Generally for an ozone system, they need what's called three-phase power, which is high voltage transmission lines. So the question would be, even if they have redundant power, how does the system deal with the loss of three-phase power? These are the big transmission line, big towers. And do they have enough emergency power to operate it? Usually, I mean, it's very power intensive. And if they cannot operate under emergency power, can they continue to operate their other treatment processes? For example, can they use chlorine to make up the difference, at least temporarily? And similar question, if it's not operating, can they meet required inactivation with their existing other chemical processes? Do they have enough of it? Can they put it in the right place? And do they have enough contact time in the clear well and other places? So, all right, other reliability considerations. Again, you need a supply of oxygen from someplace. Generally, LOX or liquid oxygen is stored on site by a vendor. So how many days of supply do they have? Do they have an alternate supplier if there's an issue with one supplier not having enough? Air prep systems, I didn't talk about, they're not as common where they're actually using compressed air. Fairly intensive maintenance schedule. Redundant equipment such as compressors, they have to dry the air before it goes in there. So those are important. And then generators, how many do they have? And how many do they keep in standby? Are they operating them all the time, or do they switch them? Can it meet expected plant flows, including one of the generators out of service for maintenance or repairs? And then we showed the tubes. The tubes have to be removed and cleaned depending on raw water quality to be effective. How do they get ozone into the water? Either fine bubble diffusers. I don't have a picture of those, but those are in the bottom of the contactor. They need to be needs to be taken out of service and cleaned for effective transfer. And those, the illustration was injecting it into a pipeline. The injectors and the mixers need to be removed. If the motor and the pump fail, you're no longer injecting ozone. So similar to what you'd look for in a chemical injection system. And then we covered this, the basics of alarms. What is monitored? Where is it monitored? When does it occur? What's the set point? And what does the operator do? Or how does the equipment respond as it's shut down? And here's some examples of things that need to be monitored or should be in an alarm system. Obviously low ozone, they're not meeting their inactivation possibly. Ozone generator, no ozone, no inactivation as well. Failures of injector pumps. And we talked about ambient ozone. That's a worker safety issue, but it would indicate there's something leaking, obviously. So with that, we'll move to questions.
Great, thank you. I will launch the first poll now. And the first one is, ozone provides a reliable disinfectant residual throughout the distribution system. True or false? And we had 67% say false.
That's correct. Ozone will come out of solution once it's exposed pretty much to atmospheric pressure, not capable of producing a residual, and it's very aggressive. A lot of the common practice is to quench ozone for other practices since it's providing minimal inactivation, and will come out of solution as soon as, for example, water hits the clear well, the ozone has come out of solution. So that's correct.
Great, the next poll has been launched, and the question is, which of the following does ozone not treat? Please select an answer. This one was a bit closer. We had 38% say bromate, and then close behind that, 30% said it treats all of these. And it looks like you.
Sorry, Mackenzie. Yes, ozone will form bromate, so it's not treating bromate.
And here is the next poll. It is another true or false. Ozone reacts with chlorine and can reduce the chlorine residual in the water. True or false? We had 75% say true.
75% got it right. It is true. It will react with chloramines. It will react with chlorine dioxide and will reduce the residual. In the case of chlorine dioxide, form a potentially regulated disinfectant byproducts. We take 10 minutes and then let Andrea finish up and go to our question and answer.
Great, wonderful.
right, I think it's about 2:16. This is Andrea Traviglia. Hello to everyone from Somerville, Massachusetts. Today, I will be talking about data integrity considerations during a sanitary survey. So up here in Region 1, we've conducted a number of sanitary survey trainings for our states over the years, and we began including a data integrity session in our trainings in 2018. So the information I'll be talking about today comes out of those training sessions based on work that was done by EPA's area-wide optimization program, EPA-OW, and relies a lot on really excellent work that was done in Washington State and published in 2014 and 2016. So I'll include specific references to this material at the end of the presentation. All right, so again, our required disclaimer language from EPA that you've seen a number of times today. I'll start with some general background information to set the stage for what I'm going to talk about, including a definition of data integrity that really sets the framework for the presentation and the considerations I'll share with respect to sanitary surveys. So when I talk about data integrity, what we're talking about is maintaining and ensuring accuracy and consistency of data over the life cycle. And by life cycle, for a water treatment plant, what that means is really from the sample collection point until the data is used and recorded. So accurate, valid data, that's the foundation of drinking water compliance and public health protection. It's another piece of that multiple barrier approach, producing safe drinking water and optimizing treatment. So this includes a number of items. I've listed a few here that I'll talk about more. The instrument selection, the maintenance and calibration of that instrument, the sample collection, both the location of it and how it is collected, and then the data collection, how that's used and how those records are maintained. So where does that fit into the sanitary survey? Well, this is a brief definition here of the sanitary survey. It's the review of these 8 elements. Clearly, data integrity is not its own element, but in many of the 8 elements, we look to the data as part of that evaluation. So we can consider what impact the accuracy and consistency of that data would have on those elements, excuse me. So I'm going to highlight specific data integrity considerations throughout this presentation for sanitary surveys. So focus today on 2 of those 8 elements of a sanitary survey: water treatment operation and drinking water compliance. Within treatment, we'll look specifically at the filtration and disinfection process. And as I'll talk about, those are clearly 2 critical pieces in the multiple barrier protection approach for safe drinking water. For data integrity considerations, for the filtration process, we'll look specifically at turbidity data, and for disinfection, CT. The second element where we'll consider data integrity today is the drinking water compliance, the monitoring compliance that's done as part of a sanitary survey review. So the data to review clearly includes the facility's compliance with the safe drinking water regulations, violations of MCLs, disinfection calculations. Have there been any changes that could affect process control or changes to water quality parameters or anything that could impact your CT requirements? So we'll focus again on filtration and disinfection and really look at, is the monitoring compliance data that's reviewed as part of the sanitary survey accurate, consistent, and what contributes and determines that. So I'll start with filtration. As I'm sure everyone on the phone knows, it's a critical barrier for public health protection. I'm really presenting this graphic here just to underscore that point. This shows the reduction of disease as a result of filtration. So presented here are typhoid deaths in Denver, Colorado. We have date on the x-axis and typhoid deaths on our 2 y-axes. And I've highlighted 2 key dates that indicate improvements to the water treatment, specifically focused on filtration. In 1893, mechanical filters were installed with a clear reduction there seen to the typhoid deaths. And then in 1937, with the completion of the filtration plant, those deaths are down to 0. So what we know are these microbial contaminants are present at these micron-sized particles. As you know, that's our turbidity measurement. And filters are the primary and physical barrier for removal of those pathogenic microorganisms. So use of a well-operated filtration process will clearly protect public health. So a key piece of the survey is to evaluate, is the filtration process performing adequately? So that in and of itself is obviously a separate training session. Today I'll talk specifically about the data behind that evaluation. So the equipment used to generate, collect the data collection process, and how that data is managed. So what I have here on this slide is a chart of the history of filtered water turbidity standards, just to demonstrate that lowered standard of turbidity over the years to where we are today. Water treatment facility staff rely on data from continuous reading turbidimeters to determine compliance with these drinking water regulatory requirements. These data also support plant process control, optimization activities everywhere, everything from evaluating performance during a filter run and the recovery period following a backwash. So a piece of this, it will be reviewed during the sanitary survey process. So as part of that compliance review conducted by the surveyor, it could include review of the state monthly operating reports, and again, looking at they're meeting all the turbidity removal requirements for that month, looking at both the individual filter effluent monitoring and combined filter effluent monitoring. So ensuring the data integrity of the turbidity data collected and used, again, that accuracy and validity of that data is key in reviewing the filtration operations. So through the next several slides, I'll outline a number of sanitary survey considerations for turbidity data integrity. So we're going to start with the equipment and look at turbidimeter operation and settings. So one consideration during a survey is to confirm turbidimeter settings are within the recommendations for signal output span and data capping, signal averaging, and loss of signal. So when I talk about signal output span and data capping, what this means is you want to avoid inappropriate capping of turbidity data that's captured by the plant's SCADA. In other words, ensuring that the system can capture true spikes in data if there are any. Clearly if that span is set to somewhere from 0 to 0.5 NTU or 0 to 1 NTU, your operators might not know how high or for how long a turbidity spike may occur. So a minimum span of 1 to at least 5.1 NTU will capture data needed for determining regulatory compliance for optimization purposes. It's also important to check for the opposite of data capping. A span set from 0 to 50 NTU or 0 to 100 NTU could also impact the accuracy of the readings, when our reg limit is 0.3. For signal averaging, there is a 30-second default that's associated with the instruments that seems to work well and usually doesn't require adjusting, so you can confirm that default setting is still set. The loss of signal gets at if the turbidimeter controller loses its signal. There are two options for how to respond. Those are the two I have there, hold output and transfer output. In the hold output mode, if the controller doesn't receive a signal from the turbidimeter, the controller will continue to send the last known value that came from the turbidimeter to SCADA. So clearly that default setting could mask a signal loss problem from operators, sometimes for days if your typical filter performance is really steady. You could have a filter that's operating at 0.2 NTU for 3 days with no change, and you might not actually realize that there could have been a loss of signal. So alternatively, the transfer output mode generates a user-defined preset value where if the signal is lost from the turbidimeter, the signal, a value that the operator has set, is one that will be immediately recognized. So maybe 0 or 5. So the operators would then be immediately aware of the problem and could address the solution. The next two here, ensuring consistent settings between instruments, fairly straightforward. The settings we just talked about ensure that all of the instruments are operating on the same span and they have the same settings. And again, ensuring that instrument flow rate is within the range recommended by the manufacturer. So we'll move from operations to maintenance of the turbidity equipment. Recommendations, considerations during sanitary survey is that the operators, the staff are adhering to the instrument maintenance schedule for those turbidimeters. For example, annual change of bulbs, inspection of photodetector, periodic sample line flushing and cleaning or replacement of that line. These pieces of the turbidimeter that can get at that accuracy and consistency of the data, that turbidity data that you need to ensure the filtration process is performing adequately. Next is turbidity sample location, ensuring appropriate location of the turbidimeters, the sample line detention times. So what I mean by that is you want to ensure representative sample is collected, and you want those turbidimeters to be as close to the sample tap as possible, ideally achieving 1 minute or less travel time to the turbidimeter. There's not a very long detention time. The sample has to flow from where the sample tap is to the turbidimeter. And next, evaluating the appropriate location of the individual filter effluent and combined filter effluent sample tap. So the IFE turbidity sample tap location, clearly you want that on the filtered water line prior to combining with water lines for other filters. And the CFE turbidity sample tap downstream of the CFE manifold. So it includes all filters, but you do want that, make sure that's upstream of the clear well and any post-filtration pH adjustment. And one example we found for a surface water system, this was actually during a file review as opposed to a sanitary survey, they had multiple exceedances of 1 NTU, and this was due in part to the CFE sample point being located after the storage tank, immediately after the filtration plant. So that storage tank sampling point could be affected by flushing hydrants near the tank and water main breaks. Presumably those occurrences stir up sediment on the bottom of the tank, which is then drawn into the distribution system and recorded at that CFE turbidimeter sampling point. So clearly it's recognized that this is probably not an accurate representation of the plant effluent turbidity, but that was the site as the CFE compliance point, and therefore they occurred violations of those turbidity requirements. So lastly, talk briefly about data management considerations for turbidity, and this is that final piece when we're talking about the life cycle of our data in a water treatment plant. Ensure that historical turbidity data are readily accessible from plant SCADA, so that this data is available to plant operators for optimization or process control purposes if they need it at any point. Conduct quality control reviews, continuous turbidimeter databases. You want to ensure that date timestamps for instruments match what's in the SCADA system record. Check that data sets that show turbidity spikes, if they're inconsistent with reported plant performance, check on that. And lastly, this is a piece that comes up, I think, in all elements of a sanitary survey is are there written SOPs available? So for many of the considerations I've mentioned, staff could develop written SOPs to ensure consistency between equipment use, maintenance, calibration, etc. Right, so we will move over to disinfection. Clearly another critical barrier in drinking water treatment. And as has been mentioned before, as the definition of disinfection, it kills and destroys a large portion of the microorganisms found in water, including most pathogens. So it's really thought to be one of the major public health advances of the 20th century, and it's the treatment process that is most often practiced at public water systems. So part of that sanitary survey, it's the one that's probably most often reviewed. First use of chlorine as a disinfectant is in the early 1900s, Jersey City, New Jersey. And to highlight that, I've included an example here from Albany, New York, that has, again, dates on the bottom, typhoid mortality on our y-axis. 1899, which is just off our chart, prior to the filtration of the public water supply, the typhoid death rate was approximately 110 per 100,000. So from 1900 to 1910, so that first decade shown here, filtration was used, and the typhoid death rate dropped to 20 per 100,000. And then starting in 1910, chlorination was introduced and optimized, and the typhoid death rate clearly drops off to 0 in the next several decades. So again, similar to filtration, review of the disinfection process during a sanitary survey is an extensive one that was covered in separate trainings, like similar to ones we had today. So today, I'll just talk about the pieces that are reviewed to highlight where data integrity considerations may be included. So again, the regulatory review or the compliance review for the disinfection process is one of those elements of the sanitary survey. So for surface water systems, treatment rules require Giardia for log virus, germ enhanced, LT1, 2-log crypto, and systems would use the CT approach and CT tables to determine an activation. I've also included groundwater systems here. I know this is a small system conference, so we want to talk about that as well. This could also be some considerations during those sanitary survey reviews. If you have groundwater systems that are providing 4-log inactivation or removal of viruses and that do conduct compliance monitoring, a survey would also require a regulatory review of the disinfection process for the groundwater rule. All right, so talking a bit about the disinfection process control, and clearly unlike earlier presentations, I'm talking specifically about chlorine as a disinfectant. So as part of a sanitary survey, you really want to talk to the operators and they should understand why and how they're disinfecting their water. And it's important to understand the amount of chlorine being added, the residual disinfectant treatment in the system to assist them as they're making any treatment changes. So within the data integrity framework, we'll look a little bit closer at that data that's being used and generated to determine the effectiveness of the disinfection process. So determination of an activation, our CT, is a bit more complex than just looking at turbidity data. So there are 3 water quality parameters: pH, temperature, and the disinfectant residual concentration, that all play a part in that first piece of the CT, that concentration piece. Included a graphic here to demonstrate pH and temperature influence on chlorine disinfection. So we have pH on the x-axis, and then the pink shaded part of the graph is the hypochlorous acid, and the yellow shaded part is hypochlorite ion. So as we see here, as pH rises above about 7.5, an increasing percentage of free chlorine is in the form of the hypochlorite ion. More HOCl, hypochlorous acid, is formed as the pH falls below 7.5. And these two species react very differently. So hypochlorous acid is 80 to 100 times more effective, and it kills microorganisms faster than your hypochlorite ions. So it's a stronger disinfectant, it's a stronger oxidizer. So temperature also influences the equilibrium here between these two species, most notably at the pH between 7 and 8. So we have 2 lines shown on here, one at 4 degrees C and one at 20 degrees C. So this again is just to demonstrate that impact of pH and temperature on our chlorine disinfectant. In general, your disinfection will be more effective at higher temperatures and lower pH. And on the time side of the equation, there are 3 factors here that I'll talk about. They're important to measure for those accurate calculations: effective volume, peak hourly flow, and the baffle factor. And I'll talk more about these in a few minutes. So with that background info, we can get into the sanitary survey considerations for disinfection data integrity. And again, I'm going to start with the measurement of CT and specifically talking about that C piece, the concentration piece. So considering the impact on disinfection effectiveness, you want to confirm that appropriate equipment or methods for those water quality parameters, pH, temperature, and disinfectant residual are being used. One example we've run into is the accuracy of equipment. A thermometer, you want a thermometer that's able to detect temperature changes of 0.1 degrees Celsius or less. If you have a thermometer that's only 1 degree increments, that might be could impact your CT calculation or your C piece of that calculation. Our temperature and pH recorded daily at the chlorine application point. And along those lines are then appropriate calibration and verification of equipment being done. Are there the use of proper reagents that are unexpired? Is calibration happening daily? Is the up-to-date meter maintenance also occurring? And are, along those lines, what I've mentioned before too, are there written SOPs for these procedures and are they being followed? So here's a quick example, just meant to demonstrate and highlight the importance of getting that pH piece right for the disinfection measurement. This was an example that was presented in the Washington State work I referenced earlier. So we have a plot of pH on the x-axis here versus contact time on the y. This is for 1 log GRD inactivation by free chlorine. So if you remember, as the pH is below 7.5, the greater percentage of the free chlorine would be hypochlorous acid, which is that stronger disinfectant. So less time is needed at lower pHs, demonstrated by this plot here. So if the measurement is taken incorrectly, here we show that the measured pH value is 7.1 versus 7.6, so it's less than the true value. That required time will be underestimated for the 1 log inactivation. So again, just really driving that point home about the importance of these water quality parameters, the equipment used to measure them, and how they're measured. Another similar example, this time looking at temperature. So again, now we have temperature on the x-axis, contact time on the y. Again, you can remember chlorine is more effective disinfectant at higher temperatures. So for this example, based on the measured temperature, it appears the contact time required would be about 50 minutes when the true value is 58. So again, if your temperature measurement is high, you're going to underestimate how much time you need. So moving to that second piece of the CT equation, time, which, the longer the time, the more effective your disinfectant process is. So the key piece of time is really T10. So T10 is that estimate of the detention time within the basin or treatment unit, in which 90% of the water passing through the unit is retained within the basin. So you want to get at 90% of that water has been treated. So to determine T10, you will need flow and volume. So start with appropriate measurements of peak hourly flow. Check how are those measured? Are they done appropriately? So the next critical piece of that would be the volume. And clear, you want to get at the specific disinfection segments that are being used for the CT calculation. So there are appropriate measurements being taken of those segments. And to that end is an appropriate baffling factor being used. So baffling factors are the estimates of short circuiting. And I have 2 examples here shown on the slide. These are generally determined by guidelines from the state or through a tracer test. So these 2 figures represent really either ends of the spectrum with respect to baffling factors. The top, the pipe flow, a baffling factor of 1 indicates, as I said, pipe flow, very high length to width with baffling. So with a baffling factor of 1, you get full credit for that volume. So what you can imagine is a slug of dye passing through this pipe. As the dye enters, it's going to move along as 1 slug through the whole pipe. So when you're looking at your T10, your contact time, your baffling factor would be 1. So you get full credit for that time. The tank underneath is a mixed basin, no baffles, with a baffling factor of 0.1. So you only get 10% credit for that volume, that entire volume. So again, if you think about the slug of dye, some's going to come in, it will exit immediately, some will stick around for a while. So when you're looking at that segment volume, you need to ensure that you're having an appropriate baffling factor. Maybe ask, how is that baffling factor selected? Lastly, as I mentioned, understanding of those disinfection segments. Are any disinfection segments not being used? Have any changes occurred since the time of the last survey that would impact that disinfection process? So again, these are all the pieces of the data that go into the measurement of that time piece for CT that can impact the accuracy, the consistency, the validity of the calculation. Again, lastly, all of that data is collected and then used in the calculation of the inactivation ratio. So what is the required inactivation? Is it being conducted daily? Is there documentation of how CT is determined in the plant? Again, are there SOPs available to explain that calculation, what the pieces are used, and is the data accurately recorded on the monthly operating reports? So to wrap this up, I just wanted to share a few EPA resources. As I mentioned at the beginning, this work, a lot of this work, the data integrity work, comes out of EPA's AWOP program. AWOP members have been examining ways to strengthen data integrity for many years, clearly with an optimization lens, an optimization framework, but a lot of the work that's been done could be incorporated into sanitary surveys. This document I reference here, generating high quality turbidity data in drinking water treatment plants to support system optimization and monitoring. This is available on the EPA website. It describes common turbidimeter setups and associated SCADA systems that are used in drinking water treatment plants and identifies best practice approaches to help ensure data quality. And coming soon, we're hoping to have available data integrity instrumentation checklists that could be used during sanitary surveys. These would provide general operational parameters, sampling considerations, reagent, and other information for several types of chlorine analyzers, as well as turbidimeters. And again, as I mentioned at the start, extensive, really excellent work has been done in Washington State, looking specifically at both disinfection and turbidity data integrity. Their work on turbidity and disinfection data integrity has been published in the journal AWWA in 2014 and 2016. They also conducted 2 data integrity webinars. These were sponsored by ASDWA. I've included the links here for their work, and I would definitely recommend checking this out if you want to dive deeper into the data integrity side of things. All right, so that's what I have, Mackenzie, if we want to go to the polling questions.
Okay, great. The first poll is data integrity is defined as maintaining and ensuring accuracy and consistency of data over its life cycle. True or false? We had 99% say true.
That was definitely a little bit of a gimme question to start off easy. Yes, it is true. That is the definition that I talked about at the start.
And the next poll has been launched. It is, which of the following is a data integrity consideration for turbidity? And 96% of the attendees said all of the above.
Man, everyone is paying attention this late in the day. I'm impressed. That's great. Yes, it is all of the above.
And then we have another true or false here. It's if the pH measurement is lower than the true value, you will overestimate the time required for inactivation. So we had about 59% say true and 41% say false.
This is actually false. So if your pH measurement is low, you will underestimate how much time you need for your CT calculation. If you remember, the lower the pH, the more effective our chlorine disinfection is.
All right, and our last poll is which of the following would be an appropriate output signal span to capture turbidity data needed for regulatory compliance? And for this one, we had 47% say 0 to 5 NTU.
Yep, and that was the answer I was looking for. Clearly the 0 to 50 is quite large and it could impact the accuracy. And then if you're looking at a 0 to 0.5 or even 0 to 1, you could cap off some of that data and miss any higher turbidity spikes that might go through your filter.
Great, thank you for those polls. Yeah, and we have a Q&A session that we can answer y'all's questions now.
Hi everyone, this is Sarah Bradbury. I'm here to help with the Q&A. So Andrea, while you're fresh, there was a question about the pH poll question you posted. If actual pH is greater than indicated, you underestimate. Reread the question.
I don't actually have it in front of me. To reread it, I apologize.
It was a true false. If the pH measurement is lower than the true value, you will overestimate the time required for inactivation.
Okay. The pH measurement is lower. Yes, you will overestimate the time.
All right.
The pH is lower, if your pH is lower, you will actually be underestimating, because as the pH is lower, you have the stronger disinfectant, that HOCl, so you won't need as much time, so you'd be underestimating.
Gotcha, thank you. So back to Jason, we had quite a few questions come in along the lines of, was your app developed by a contractor, wanting to know what the cost was? Is it specific to Pennsylvania, or are other states using it, or would it be available somehow? So kind of along the lines of what's the availability? People like your app.
Yeah, well, that's good. Thank you. So our app was developed internally by contractors. And since we're a SIDWIS-free state, our data, like our SIDWINS data and stuff, but other states would consider SIDWINS data, it looks pretty different. So it's not, so this app wouldn't be like easily transferred to another state. It would probably take a good bit of work, because unfortunately it's communicating with our data systems, which don't look like anybody else's data systems. Cost is really hard to say, just because of the way we do IT costs in Pennsylvania, because some of them are done through, some of the work was done through specific contractors who were being paid out of pots of money for this specific job, and other ones were kind of more of the general IT contractor or IT staff. So I can't put a good number on it, but I will say for sure it was not cheap. And it took several developers a good bit of time to put it together. And like I said, we're still not exactly happy with where it is. So it's not done as far as we're concerned. And we expect to spend, well over $100,000 to get it to the point where we're happy with it. So it was an expensive process.
Gotcha, thank you. Next question is for Mike. How often do utilities need to perform direct integrity testing?
The recommendation or the requirement under the rules is every 24 hours. However, the state has the option to modify that.
Gotcha. Thank you. All right, next question is for Eugene. For arsenic treatment, what is the recommended resin, and are there any special considerations for such treatment? What is the recommended method for monitoring performance?
So for the resin, there are many manufacturers. So I think the best is to reach out to the resin manufacturers' websites. So there's Purolite, there's EPA-OW, and a lot of other companies. So I recommend that you reach out to the resin manufacturer. The best information is give them the raw water quality data. They'll be able to ask you what is the parameters that they need to run their model. And then so that you can actually, the water system should reach out to different resin manufacturers, the technical assistance department. They should be able to recommend what resin will work best based on their raw water quality. Resin is very proprietary, so it's very difficult for me to recommend a specific resin. So work with the tech support on the resin retailer or the manufacturer. They should be able to help. And for the performance monitoring, very much like, so for arsenic treatment, compliance is based on the running annual average. So it really depends on your state's tolerance for water being served to the public that's over the MCL, because there is like averaging going on, that if you have a product tank and everything, so it's very site specific. But if it's in California, we really want people to operate on a tight operation. So we want them to have samples collected prior to storage, so that we make sure that all water entering the storage tank is below the MCL. And I will use the same philosophy, monitor it before regeneration periodically to make sure that it's working well. And in California, regulations is for anyone that provides treatment is monthly regulatory sample, and then we use those to determine compliance with the MCL, and then do those recommended extra samples to see if they're regenerate at the right time. So that's what I would recommend.
All right, thank you. Next question is for Karen. Are both UV and chlorine as backup recommended? And if so, where should the chlorine injection be introduced?
I'm not sure what you mean by as backup. If one should be backing up the other. For small systems, you don't see it that often, except if they need to maintain a residual out in the distribution system. I mean, it seems like it's one or the other, really. I don't know, Mike, you want to weigh in on that?
Yeah, I would agree. The only issue, the real issue with small systems is that the off-the-shelf UVs that they often put in, they're like 40 millijoules, which is great if you're trying to get rid of address cryptosporidium, but pretty much useless if you're trying to deal with virus. So
yeah. So it's not really a backup setup. You know, you will see the combo, but it's really because they're trying to get the viruses as well with the chlorine.
So Mike, it's Eugene. I think one of the approach in California is like if the system has a UV reactor after the filtered water, if the system fails, we will allow them temporarily to do pre-chlorination so that the chlorine will run through the entire treatment plant so that there's more CT and they're able to meet it to keep the water safe while they figure out what's wrong with the UV reactor. Maybe that's where the audience is asking the question is coming from.
So you have to have at the ready your CT calculations. You need to talk to Andrea. Yeah, make sure that they have good CT calculations, right?
Right, because we have a lot of power glitch, as you know, with our fires. So we have system ready for the chlorinators so that they can, if the system back up, they can fire up the chlorine and do pre-chlorination while they wait for power to be restored or something, and they can continue to provide safe water.
Right.
All right, thanks, y'all. Next question for Andrea. For Giardia, although also there was a note to wish you a happy belated birthday. So the question is, for Giardia inactivation, does it have to happen after filtration, or can it occur in the sedimentation basins?
I'm not sure how that relates exactly to data integrity.
Maybe that was meant for someone else. I don't know.
Can you read the question again?
Sure. For Giardia inactivation, does it have to happen after filtration, or can it occur in the sedimentation basins?
Well, along the line, I guess, Eugene, if you guys are saying it's okay to pre-chlorinate and cover, it's whether you get CT credit during your treatment train or not.
Right. In California, we do give CT credit through the entire treatment train from the headworks onwards. Prior to DBP rules, we allowed that, and people generally operate at CT much higher than what's required of 3 log Giardia. So it's been done in the past, and we give them credit in California.
Thanks, Eugene.
All right. Oops, any more on that one? Okay.
Because
So-
it does
go
point
ahead,
to
Mike.
how often you're monitoring though, because I mean you're in the sedimentation based on the turbidity is not always constant. It could be high. So that's going to interfere. So if they're going to give them credit for it, you know, if they're going to get credit for it, they got to measure it. So.
Right.
All right, so here's a data integrity question. Is there a concern for falsified data, Andrea?
Yes. I mean, that's clearly a concern. I think that's something that is great to evaluate when you're out there during the sanitary survey, that the data that they're recording actually makes sense and that they understand how they're recording it to get at that. I didn't
Gotcha.
cover it. Yeah, I didn't cover it clearly today, but I think that's always a concern.
Gotcha. All right, back to Jason. Let's see. Do you have any lesson learned by developing your app? Or while you,
Yeah.
or what you were looking at it while you were creating it?
Yeah, a lot. I think one of the biggest was, I don't think any of us really thought how much work was going to go into it. So like when you talk about costs, I was talking about contractor costs, but there was a lot of safe drinking water staff time that went into it as well. We had daily meetings for quite a while as the development was ongoing. So just recognizing how much time that you're going to put into developing an app like that is huge. Another thing is, you know, make sure you work with your field staff so that you are building something that they can use. If you're just letting IT kind of drive that bus, it might not work out as well. So be sure to involve all the parties. And I think just one last, and again, I could go on forever. One last thing is just be flexible, because probably the app that gets developed is not going to do exactly what you want it to do, especially the first time around. So be willing to be flexible and continue to work with your IT people to get what you're looking for. And that's even with after developing pretty specific guidelines for what we were looking for. So just be ready to be flexible.
Good advice. All right, Mike, here's a question from your ozone presentation. Is hydrogen a byproduct of ozone generation?
Hydrogen a byproduct of ozone generation. Well, hydrogen is generated by any oxidation process. So yes, I guess, yeah. You're oxidizing anything, you're oxidizing water, you're removing, yeah. But it wouldn't be any different than any other oxidation process, so no. It's not really a factor in disinfection byproducts. It's not really a factor. Remember, you know, everything in a pressurized system, everything is in solution. So.
Gotcha. Thanks, Mike. I just wanted to note that there were several people that noted that they were appreciative of the presentations and that they were very helpful. And Mackenzie, should we close it out? We didn't get a chance to get to all the questions, unfortunately. We ran out of time.
Yeah, I think all the presenters have graciously agreed to answer questions after the fact, as much time as all of us have, since we have other responsibilities too. So we will keep track of them, and we'll try to get answers to all of those folks that are in the question box, I guess. With that, we're at 3 o'clock. It looks like I want to say thank you. People are starting to drop off, but I want to say thank you. It looks like about 600 of you were better, stayed with us to the very end here, and it was a long, long day. So, yeah. What else? So I'm glad this worked out. You know, this is our first time trying to do this way. This is a new way of doing things. I think my concern about glitches was overblown, but that's just what's new for me anyway. What else? And you know, everybody took the time to volunteer, and participate, and I know it was a lot of work to get presentations done. So Jason, Andrea, Karen, Eugene, thank you for putting the time in to get this together. That means that you're on the hook for next year too. Who else? Sarah, who is our coworker in Washington. Sarah, thank you for handling the questions. Mackenzie, we could not have done it without you. Thank you. And I think that's all I have. As you know, the small water system workshop goes on for the next few days. Lots of information. So, and the good news is that you don't have to convince somebody to let you travel. So I would encourage you to take advantage of what's going on. And with that, keep up the good work, folks. Thank you, everybody.
Bye-bye.
Bye, everyone. Stay safe and healthy.
Thank you. Goodbye.